We are delighted to invite you to be part of the second day of the ATAL Faculty Development Program, which brings together academia and industry experts to share knowledge, insights, and emerging perspectives in the field of semiconductor technologies.
This faculty development program is a pivotal initiative in the context of India's rapidly evolving semiconductor landscape, which is poised to emerge as a global leader in chip design, manufacturing, and innovation. As India strengthens its semiconductor mission, developing a strong understanding of technologies spanning design to packaging has become essential.
The FDP offers comprehensive exposure to critical areas such as cleanroom technologies, vacuum systems, and semiconductor fabrication processes, including lithography and etching, along with advanced topics like EDA tools, AI, and machine learning applications in VLSI, and the complete design flow from RTL to GDS2.
In addition, participants will explore semiconductor packaging, nanomaterials, and analog and mixed signal VLSI design, gaining insights into both foundational and advanced aspects of semiconductor engineering.
Through expert led sessions on global market trends, India's semiconductor assembly and testing ecosystems, and emerging industry developments combined with interactive discussions and practical insights. This FTP aims to strengthen research capabilities, teaching excellence, and industry collaboration, contributing meaningfully to India's vision of self reliance in semiconductors. It is now our privilege to invite our first speaker for the day, Professor J.P. Singh from the Indian Institute of Technology, Delhi.
Professor Singh is the head of the Nanoscale Research Facility, GLAD, and Nano CVD Laboratory at IIT Delhi, and an internationally recognized researcher in nanostructures, advanced materials, and cleanroom-enabled fabrication technologies. Professor Singh has made significant contributions to nanoscale materials research, serves as an associate editor of Advanced Materials Letters, is a research advisor at Nanyang Academy of Sciences, Singapore, and is a fellow of the International Association of Advanced Materials.
With extensive research publications, global collaborations, and leadership in advanced laboratory facilities, he will now deliver Technical Session 3 on clean room technologies. We invite Professor J.P. Singh to kindly begin the session. The chat box will remain open and Q&A will be taken at the end. With this, I extend a warm welcome and over to you, sir.
Yeah, thank you. Can you hear me?
Yes, sir.
Yes, sir.
Okay. So yeah, so thanks for the introduction, and I'm really thankful for the organizer to give me kind invitation. So just to deliver a talk on clean room facility. So let me know if you can see the slide. Maybe
Yes,
full,
sir, we
it's
can
full
see the
screen.
slides.
Okay, full screen. Okay. So yeah, so we have like here in nanoscale research facility where we have the clean room facility. So I'll just go through some basics of clean room. What do we mean by the clean room? And then because there are many more facilities which are involved in the clean room for the processing where we process devices. Uh, HEMT and other like quantum devices. But I will today, because of the time limit, I will only talk about basically the facility, like the basics of the clean room. What is clean room? So I'll try to introduce you the clean room, and then a little bit about the lithography facility which are normally used in the clean room. Then some examples which I will give you, the maskless lithography, as well as basically the conventional deposition system which we have here. So so what do we mean by a clean room? What is a clean room? So clean room means it is a controlled environment. So where we fabricate the devices, we process the device, and so the clean room means it has a controlled environment. There are very low contamination. When we talk about the contamination in the device fabrication, it is mainly that we talk about the dust, airborne chemical vapors, and there are others maybe. including humidity also. And then those are the contaminations which we don't want while basically fabricating the device, because the device size is very very small. Now we are approaching to small nanometer size devices. So these contaminations can basically hinder the fabrication of the device. So let me just turn on basically the pointer here. Yeah. So like you can see, I have shown you two clean room where it is classified like class 100 clean room. So this yellow color room, like this is a class 100, where you can see our like electron beam lithography is already there, and there is a photolithography setup also here. And then there is a class 1000 clean room where we have mask aligner, wire bounder, and other oxidation furnace you can see here. So all devices are here. So, but first of all, what we mean by how we classify the clean room? Like I'm just saying class 100, what does it mean actually? So when we say class 100 clean room, it means there are less than 100 particles per cubic feet in which the particle size which are having more than 0.5 micron. So means class 100 clean room has particles size which are more than 0.5 macrons. They are only less than 100 particles. Then we say it is the class 100 clean room. Same way, like class 1000, you can define class 10. So normally for the device fabrication, for actual device transistors and devices for fabrication of quantum device, we prefer class 100 or class 10 clean room. So here in this slide, you can see I'm just showing you basically the classification of the clean room. So you can see here the different classes are defined from class 1 to 10,000 and more than that actually. And so the same, like you just see this column where it is the definition is in such a way that I'm just taking like 0.5 macron size bigger particle, and if they are more than 100, less than 100 particle, we say it's a class 100. And there is ISO standard also. Sometimes people say it is ISO 5 or ISO 6. So this is the classification of the clean room. Now, what facilities normally in the clean room we can see here, like for where we talk about the semiconductor device fabrication. So you can see basically the facility like we have is electron beam lithography, where you can just use this lithography for devices which are up to 10 nanometer or of the order of 10 nanometer or so. Or there are some devices you can also see like PECVD, plasma enhanced CVD, or reactive ion etching. These are the technology, or E-beam evaporator for the metallization, or you can see sputtering. This is also for contact deposition, and there are the mask aligner, and there are other facilities which I'm listing here, like oxidation furnace for making a uniform oxide layer and control thickness. And there are other facilities like atomic layer deposition or thermal evaporator. Atomic layer deposition means sometimes we need a very thin layer like monolayer deposition. So then we talk about the atomic layer deposition. Now, so first of all, like now we talk about in the clean room, like what are the sources of contaminants actually. So you see I'm just linking basically there are many sources of contaminants, mainly three. So first is the molecular contaminants. So this molecular contaminants means the contamination can come from the outgassing, like like if there is some paint actually, you see if like there is a paint or there are some chemicals which are there, so that there might be some vapors which are coming out, or maybe all the materials at they can actually there is some gases which are coming out from the materials, and so there is like a desorption of the gases from the material, and those gases can be a contaminant for the clean room where you fabricate your device. Or there might be some oil vapors if you are using, like if you are using various pumps here, like diffusion. Normally diffusion we don't use, but a rotary pump, or so diaphragm rotary, or so there might be some oil which we are using. Those oil vapors can also be a source of contamination. See, when we talk about like there is only we only allow less than 100 particles per cubic feet. It's a very small number. So So means this small amount of the contamination can also basically disturb the devices. So there are like glues, epoxies which are used, and aromatic means there might be many sources of contaminants which are molecular nature, or there might be surface contamination also, like the like I'm just showing you here a desk here where say there's a glove box where you fabricate the device inside some controlled environment, but there is a workstation, workbench where which can get contaminated. And you see one of the major contamination is basically our uh, like the fingerprints, which because our like in the hands you see there is a oil secretion is there, is the oil and grease which comes out from the body, and that is very sticky. So once it is there, it's very difficult to take that out because it is a source of basically molecular, like a source of the contamination. Skin oil and hand cream, face cream, polish, so those all be can be the source of the contamination inside the clean room. The other source of contaminants which are basically I think the most important contaminant is the person himself, like the people who are actually working inside the clean room. So you see we also shred a lot of particles. We don't care actually in the normal environment, but when you are talking about class 100 or class 10 environment where we can only allow like we only need less than 10 particles per cubic feet or less than 100 particle per cubic feet, then basically this is very important because uh, there are a lot of contaminants from the person itself, like skin, hair, clothing, lint. Those are also kind of contaminants. And there are some particle shredding materials also, like cardboard boxes, paper. Even when we use the normal paper actually, which is they can also be a source of contamination. So inside the clean room, we actually take care of all these things, even including the paper, pen, whatever things we are actually taking care of. They are different. They are not the regular conventional things which we can bring inside the clean room, because that can be also a source of contaminant. They can actually shred particulates actually inside in the air actually. And there might be some braiding action. Normally we avoid these kind of things like drilling, sanding, sawing, so or the bare wood products. So normally we use all metal systems there inside the clean room, because the bare wood products can also be a source of contaminants. They can also dissolve basically contaminate particulates inside the air. So now let me just talk about basically what does it mean by particle more than 0.5 micron, because that was in the definition. So you see, I'm just talking about, you can see here. So so this the black one is the diamond is the human hair. You can see the size of the human hair. So the human hair, the size is about 100 micron, and then basically this white dot is a small white dot is basically in the same scale, so 0.5 macron thickness. So you can see here basically, so normally anything more than 50 micron is normally visible to eye, and this size 0.5 macron is like is much smaller than that. So you can see it's like more than 100 times smaller than that. So these actually particulates are very small, so they cannot be actually seen by the naked eyes. So we need so that's why it's very difficult actually to control those things. And most of these particles are too small, and then mostly they actually bound with the surface by the electrostatic bonding. There's a charge. They get charged, and then because of the dipole interaction, they get basically attached to the surfaces. So, so this is something like I'm just talking about the size which which you can just think about, like when I'm saying particles more than 0.5 microns. So what does it mean actually? If we compare with the human hair. Now, the relative size of the common airborne contaminants, which is we can just say, which we talk about inside the clean room. So you can see here the human hair is about 100 micron, like something like 60 to more than 100 micron, depending person to person, it varies. And then you see the size of when we go to very small size, like 0.5 something here, like this is 0.1 micron. So 0.1 micron means like virus is about 100 nanometer size, so it is of that order. Bacteria is few microns. Even bacteria is more than basically 0.5, which is around 10 microns. So when we talk about basically the particles, so we only allow less than basically more than 0.5 micron, which is less than number is less than 100 actually. So this picture just gives you some kind of a relative idea like what is the size we are talking about. So actually when we talk about 0.5 micron or less than that, we cannot see by the normal optical microscope. It has to be through scanning electron microscope or maybe the other techniques which microscopy we have to use to even see those things. Now this very interesting uh, picture here you can see. So in this this is the IC actually. This is IC. You can see there are many contacts are there, and this is basically a real picture of an IC where thousands of transistors are fabricated on the basically the semiconductor surface, and there is a here somehow one like here actually which actually get just get landed on this IC surface. So you can see here. So what does it mean actually when you are working in the such clean environment, and even a single hair can actually destroy your basically your the semiconductor device actually. So this is the picture. This is a real picture of here, and then with the IC surface. Now, major contamination source, if I talk about in the clean room, is the people themselves. Actually, there's like mostly when we work in the clean room, the 75% of the contamination comes because of the person who are working inside the clean room. That's why what happens actually in the clean room, we normally restrict the entry. There is a very restriction of the entry for the people who are moving inside the clean room. So we actually monitor the number of person who are working at a time inside the clean room so that we can control the contamination. Other thing is the ventilation, which ventilation room structure equipment, which is comparatively much smaller. So the human itself is the major source of the contamination. Now, when we are working inside the clean room, we are the primary contaminants. And also you can see here, I'm just showing you basically how many number of particles per minute, which is greater than 0.3 micron is shed by the person who are working inside the clean room. So you see, just giving you the, depending on the nature of the activity, the particles inside the clean room, the number of particles inside the clean room can go very, very high actually. You see, so that's why we limit our activity also inside the clean room while basically fabricating the devices, so that actually we can just control the contaminant inside the clean room. So overall, when you see basically people who are actually working in the semiconductor fabrication, and then you see mostly they are wearing this kind of suit here, which is very special. And actually the idea is actually this is a very special suit which is which covered mostly all the body parts. You can see here, so it's covered all the body parts, and then there is a shoe here including head cover, safety glasses are there, and mask is also there. So that actually when you enter inside the clean room, so we have basically the air shower, so that when you go inside the clean room, and then we can say basically uh, uh, we can just say okay, we are not actually contamination. We can restrict the contamination inside the clean room. So that is something like when you go inside the clean room, how you have to properly dress up. You see the people are dress up inside, and then also we limit the time, how much time we are actually spending inside the clean room. We only go when all the when it is needed inside the clean room. So that's why for all the clean rooms, they have the entry and the exit log. So we have, and also there are we also monitor basically their activity inside the clean room. So that is something giving you the idea about the clean room, like what does it mean by the clean room, and then what type of normally basically activities one can do inside the clean room. And let me give you one idea. I think let me just okay, wait for a second. Yeah. So So here you see, I'm just giving you basically, I'm just showing you kind of uh, like the size distribution of particles when actually a person sneeze or cough. So that's just giving you some idea, like while inside the clean room, if someone actually sneezes or cough, then how much basically contamination is there actually. So it's like it's a statistical we just get from so this you can see here. So sneezing while like one time sneezing, you see it gives like some 800,000 actually particles which are coming out compared to the cup which is 66,000. So inside, that's why we use the double layer kind of like the mask also inside the clean room, because the you see the number of particles which are coming out of basically the sneezing, because the sneezing or coughing is also very high here. So so this is a little bit like giving you the idea, like when you work inside the clean room, you have to one has to it's like important to wear all the this like suits and properly covered, and also in the correct manner actually, so that you really cover all of your body parts while actually going inside the clean room. Now I'll talk about basically the facilities which are actually inside the clean room. So here I'll just talk about some lithography techniques which we use inside the clean room. So basically nowadays actually we fabricate nanostructures like transistors or nano devices using under inside the clean room. So so mostly for the lithography, so there are two approaches to form the nano devices. One is basically the top-down approach. Another is the bottom-up approach. Top-down approach means basically we just use the lithography method. We just use the patterning and then make the devices there. Bottom-up approach means it uses basically the technique like some kind of like the either CVD, CVD, plasma enhanced CVD, or physical vapor deposition, these kind of methods we use for the bottom-up approach. Now, so the lithography process is basically your top-down approach. So what happens inside the lithography process? So in lithography process, basically we create the nano devices by we make some pattern actually on the substrate. So how do we make the pattern? We just these patterns were made by creation of some kind of resist on the substrate. I'll show you in the next slide, and then basically like I can show you here. So we use a substrate here. Then we just coat the substrate with a resist. I'll talk about what is the resist like just after some time. Like I'll just talk after this slide. I'll let you know. And then we put a mask here. So mask is a physical mask, like sometime like we fabricate by this mask by some other techniques, like this can be a steel mask, and then this this whole structure is basically like irradiated. Now so you see here, so so this irradiation is done by different kind of like the methods. One can use basically the visible light or the ultraviolet or X-ray or electron or ion. So these actually are the radiation sources which basically which actually which are actually impingent on the photoresist material. So photoresist material, this resist material is nothing but it is some kind of polymer, or sometimes it is a metal oxides also. So this polymer actually its property is in such a way that when actually it like it undergoes some kind of irradiation, then it is actually chemically changed. So so there are two types of photoresist we talk about. One is the positive resist, other is the negative resist. So positive resist means the irradiated area, means you see like in this case, you see if I'm using some hard mask here, when you shine, suppose I shine some UV light here, so UV light it will only pass between the window, which is the mask, which is the open area, and then so this area which is under the open window of the mask will actually come under the irradiation of the ultraviolet light, and this light will what this light will do, then it will change the resist material, chemically change the resist material. So in case of positive resist, if we are using the positive resist, this area will be more soluble, means this area will become more soluble compared to the other area. So we call it like a positive resist. While in this case of negative resist, if I say, the area becomes much hardened, so that will be kind of insoluble. So this is like the the types of I say the two types of photoresist we use, and one of the photoresist which is mainly used. And now photoresist also is basically particular for the particular type of technique. Like if I'm using a UV, suppose UV radiation of 365 nanometer, then normally we use SU8, which is a very common kind of a photoresist which is used in the lithography process. Now, so there are now one can ask, like there are different kind of techniques one can use. I can use the visible light, UV light, X-ray, or electron, or ion. So now which one has to use for the lithography process? Now it depends on the basically your the resolution here. So see, if I'm using a mask here, now you see basically the resolution. If I talk about, so if I'm using the visible light, the visible light, you see the wavelength will be somewhere between the 400 nanometer to 800 nanometer. So means if you want basically some kind of like the structure, you see we cannot get actually better than that, because it's a diffraction limited here also, because the light can go, light can actually go like it, because of diffraction, the light can actually will go actually, it won't be a kind of a step kind of structure. Light will go actually pass through the region which is under the mask also, because of the diffraction only. So because of that actually, so the resolution will define this UV, or the selection of these things actually is because of the resolution, how much resolution we need actually. Like if I go for the electron beam lithography, you can get up to 10 nanometer. I know I'm talking about basically the visible light. So normally the practical thing is up to like few microns only you can get. UV, like some micron you can get. So this is like the type of the lithography used. And the name of the lithography is also normally given by the type of the irradiation we use. So sometimes when we say it's a photolithography, it means you are using the visible light. Electron beam lithography means the irradiation by the electron beam actually. Now, now there are other techniques. So this is the idea I'm giving you about the very general about the lithography, and then there is another technique which is like past like 2 decades, or like more than like about 2 decades, which is actually in the market, which we call is nano imprint technology. So nano imprint technology is like where is basically where we don't use any kind of photoresist, it's like a kind of a stamp, mold or stamp we use, and then you just directly put on the substrate and you press it. So like in this case, like in this way actually. So you have a mold here, we have a resist here. So without using any kind of irradiation here, we don't use like any irradiation, and whatever is the mold, you can get a negative imprint on the resist just by basically you just press the mold against the substrate where we have a register. So you can get a pattern here actually. But this technique looks very simple, but it is mainly for the polymer kind of the structures. If you want to fabricate, then these are actually more useful. But kind of the devices, if you want to fabricate like on silicon and the, so it's not that much actually useful for the semiconductor material. But there is other technique also, like we have in our lab, like maskless photolithography. Maskless means we don't use any kind of like mask here, because you remember when we talk about the uh, like the lithography process, I told you we just first coat with the resist and then we put some physical mask here. So this is a very big limitation here, because depending on the shape of the mask, only you get basically the pattern on the substrate. So if you have a square mask, or if you have a triangular mask or circular mask, or the different, if I want to change basically the size of the window, then you have to make we have to fabricate those kind of a hard mask, like steel hard mask with different techniques, which is very tricky. So one of the technique which actually allows basically where we don't use the physical mask, which is the direct lithography, is the maskless lithography. So this is the maskless lithography, and what is actually there in the maskless lithography? We use basically the resist, but instead of like mask, we just directly put the pattern by making some kind of a structure, whatever whatever pattern you want, we can make a CAD file of that. And then there are very tiny micro, you say, in case of, if it is in our case for like a photolithography, so there are many tiny mirror systems are there, so which actually either allow the laser which falls on the substrate, or maybe there are mirrors which can actually take away light from the register itself. So means we just control basically the light on and off over the surface, over this register surface, like here over the register surface. Instead of mask, we just physically use the mirror system in the machine, such that the light will fall, or it will fall on the surface, or it won't fall on the surface. So this we control very accurately by using basically some kind of a digital mask, which control basically the position of the laser, or maybe the position of the which is falling on the register actually. So but it's a very kind of like the very accurate positioning is there, and then by that actually we can fabricate the pattern, which by the maskless method. And like I just showed you basically like SU8 I just talked about. So there's a SU8 series is there, and there are, so you can use either, basically you can use either positive photoresist, or you can use either negative photoresist. So then we don't need any hard mask for patterning. This is a very one of the very big advantage here, because fabricating the mask for the pattern is one of the big challenge actually, because every time if you want to change the pattern, then you have to change the mask, your hard mask itself. And it can go to the full large wafer, like in one go you can just fabricate the devices pattern over the 6-inch wafer in one go also. So it's like a very this technique is like suited for the wafer scale also. Now there are some so that is like lithography we talk about. That is something like the technique where you see we use the top-down approach, means starting from the photoresist, then we fabricate the pattern using different kind of lithography. You can use lithography depending on the resolution we want. So we can, if we really want like some like nanometer or that kind of resolution, we can go by electron beam lithography. Or if our pattern size is up to a few microns, then we can go for photolithography, or we can use ultraviolet UV lithography also. So that was top down approach. Then bottom up approach means there are means like means in bottom approach means like we can just fabricate the maybe the pattern or the structure from from atom to atom, like attaching one atom to other atom, and then fabricating the device or pattern. That is another idea, that is which we use for the bottom up approach. So you see like the technique which we use is like physical vapor deposition is one of the technique here. So in physical vapor deposition, what is actually happening? We just convert the solid material into the gaseous phase by some physical process. So what is that physical process? Means that can be either we can sublimate our material by using electron beam heating. So or we can use the laser ablation. We can shine the laser on the material and it can sublimate to the gaseous state. Or we can use some kind of sputtering, means here we use basically the energized ions which actually get bombarded on the target material, and then you can just remove the target material. It can get further deposited on the substrate actually. So there are different kind of methods which comes under the class of physical vapor deposition, but it is actually by atom to atom. All these methods, the deposition is by atom to atom. So like one example which I'm giving you, which we normally use for basically for the coating or for contact fabrication is the magnetron sputtering process. So what is actually here in the case of magnetron sputtering, you use basically the substrate. This is my substrate, which is one of the electrode, and in other electrode we use basically our target. So target is the material which you want to deposit. Suppose I want to deposit chromium or gold actually. So this, or platinum. So this will be the target material. My target material will be like platinum, platinum target. And then what happens actually, then we in between that we create some vacuum, and then we put some kind of carrier gas. So which is this which we want to make a plasma for that. So you just suppose normally we put like argon. So you can just, because argon is like inert, so it doesn't get actually make any chemical reaction with my target material, or it won't make any chemical residue with my substrate. So that is one of the advantage of that. Then we apply basically high voltage between the positive, between the anode and the cathode. With the anode, your cathode is substrate, anode is target material, and then we create basically. So you apply the very high voltage between them. Then what happens? Then basically at a certain voltage, and by actually optimizing the pressure inside the argon gas, then basically there is a corona discharge, which means that your argon atom can actually ionize, and then atom can become argon ion now. And these argon ions, like which are positive, actually they will depending on basically, see, it's a negative, so they actually are going to bombard your target, and then target will be basically, which is the platinum atom, which, so because of sputtering, this target actually can be target atoms can dislodge from the from the target material. So means like so this atom, like if it is a platinum, platinum will get dislodged, and the platinum atom will come out from the target material, and they because then they slowly actually get deposited over your substrate material. So this is the very rough idea I gave you, basically how this sputtering works. Uh, Other, you see, we use the magnets also. We call it magnetron sputtering. So this is a DC sputtering I talk about. There is another RF sputtering. I didn't talk about that also. But in the magnetron sputtering, we use magnets. So the idea of the magnet is basically, you see, when you have the magnetic field, then you know that when charged particle is moving in the magnetic field, the magnetic force actually is perpendicular to the direction of the magnetic field. So it makes some kind of a helical motion. So means we can increase the path of these ions, so that actually so that actually number of argon ions creation will be more, because there will be more like electrons will be more actually getting they actually getting basically the argon ions will be more ionized in this way, and you increase the number of argon ions. So more the argon ions, and then the more the number of the target material which dislodge from the from the target actually, and then you get basically higher deposition rate. So that is, in this case, normally the deposition rate is high compared to the other techniques like the thermal deposition or e-beam deposition. The deposition rate normally is 1 micrometer per minute. It's a typical number I'm giving you. And then you see there is some kind of a rotation assembly also, which rotates this target with respect to the substrate. The idea is so that actually the argon ion should not actually get actually just hit at one place, and you want actually a kind of a uniform coating of your substrate. So that is the idea. Now, the physical deposition which we just talk about actually, so one has to be very careful. Like in this case, the starting material has to be very high purity material. Like if you are using the target material needs to be it has to be very kind of like very pure. And when we talk about the purity, we talk about like how many number of n's are there. If I say 2n purity, it is 99.99% pure. So because the purity of the material is very, very important here when you are using the physical vapor deposition. And in this case, for the physical vapor depositions, normally we deposit metals, but we also deposit dielectric material also. Like in case of sputtering, normally we use the dielectric materials also. But here one thing is very important: there is no chemical reaction involved here. So there is no chemical reaction involved here. Like it's just the basically like if it is the electron beam deposition, it's just the sublimation, means like from the solid to the vapor phase material goes there. Now, so in case of so there are many methods here. So I'm just giving you the idea, advantage of because if I use basically the thermal deposition, where you thermally evaporate the material, and so in the case of case of normal deposition, you see it's a normal e-beam deposition, then you get basically this is the coverage. Like this is the suppose some film which get deposited on the pattern here. We suppose we are depositing, but the problem will be the side wall. You see the side wall will be spotty, so it won't be deposited well here if we use the kind of a normal like thermal deposition. But if you go by the sputtering system, so normally sputtering system, because ions are actually hitting from all the places and they are actually coming towards the substrate, towards the substrate fill all the direction it has some, so they actually deposit very well. So in case of sputtering, it's a very useful technique. You can see you get basically a continuous film on the side wall also. So that is the one of the advantage here. Now we talk about basically little more physics about that, actually, like how the deposition happens. Like one can think of like, can we deposit the film in atmospheric condition, or we need vacuum actually? So see, the reason actually why we cannot do all this kind of deposition in the atmospheric condition. So you see, if I talk about, so there's a word mean free path. So mean free path means, you see, if I talk about the mean free path means between any two successive collision, what is the length of which is traveled by the molecule. So if I just talk about in the air, you have mainly the nitrogen. You see the gas molecules are moving from, so means between two any successive collisions, what is the length? So if I talk about the atmospheric pressure, which is 760 torr, so you see normally the mean free path is of the order of 40 nanometer. It's a very, very nanometer size only. So which is basically kind of like the very, very small. So it is even less than that actually. So means, so you see when we have the substrate which is there, you see in this case substrate or the target. So this distance is normally few centimeters, few tens of centimeter, around 20 centimeter or more than basically 10 centimeter. So you see in this case the mean free path is 40 nanometers. So it means you won't get basically the meaningful deposition when you are doing in the atmospheric pressure. So you see, if I reduce the pressure, if I go for the low vacuum, which we call like 0.76 torr, then you see basically I don't talk about basically the relation, but the pressure and mean free path are inversely proportional. So when you just go for basically the lower pressure, the mean free path actually increases. So it becomes like 0.76 torr, which you call low vacuum, is mean free path becomes 40 micrometer, and for 76 millitorr it becomes 4 millimeter, and for high vacuum, which normally we work by like 7.6 microtorr, something 10 raised to power minus 6 torr we work. So there you see the mean free path is 4 meter. What does it mean? It means basically two molecules, because your size of the chamber will is normally much smaller. Chamber size is something like less than a meter actually. So basically it means that see, these atoms are not colliding with the other molecule, but they are colliding mainly with the chamber surface only, and we cool the chamber surface, so when they are colliding, mostly they get absorbed there. So so it means you avoid basically the interparticle in like molecular collision among themselves actually. So that will be some kind of a line of sight kind of deposition in case of physical vapor deposition. So whatever molecules are coming from there, they will directly come and deposit on the substrate. So that is the idea, like why you have to use basically the high vacuum in the deposition systems. So and also all techniques, like either use, we have just gave you the example of sputtering technique, but if you go for the thermal deposition or electron beam deposition, like all these deposition in physical vapor deposition, the evaporated materials, they travel straight to the wafer. That is, we call a line of sight. Okay, so this is very, very directional actually. Okay. Now, now I'll just talk about basically the the contamination also. So the other like I say, the other the reason why we use basically deposition inside the vacuum chamber, we want a very good vacuum. So Now you see the high vacuum is good enough, but normally we go for the ultra high vacuum also, like we just talked about 10 raised to power minus 9 torr also. So it's a very, we call it like ultra high vacuum, like high vacuum 10 raised to power minus 6. And if you go up to the limit like 10 to power minus 9 or better than that, we call it ultra high vacuum. So what happens actually, you see, like if I just say you have a surface, so in air there is always some humidity, and you see the water molecules are there. So if I talk about the water molecules, so those are actually the polar molecules. So water is having a very high dielectric constant. So it's so what happens actually, because of the polar nature, these water molecules or other contaminants, they get dipole interaction with the surfaces. Even surface is not charged, but there might be some dipole interaction. Because of that, the most of the surfaces you see, they will always be covered by a very thin layer of water layer. So which we call like humidity, like there will be some water patches on your surfaces, or there will be some contaminants, vapor species also, or some other contaminants, dust or some other maybe contaminants which are there in, or other gases which you talk about, which you don't want. But like oxygen is one of the gas, most of your surfaces get oxidized also, because oxygen randomly they actually land on the surface. They can react on the silicon and form some silicon dioxide, or for other materials also it can make some oxidation, like whatever context you are making, that can also get oxidized. So one of the idea is, see, if I just talk about basically, then we talk about the monolayer formation. What is the meaning of monolayer? Monolayer means, if suppose you want to cover your surface with one atomic layer thickness, with one atom thickness, you complete your surface. So if I say, if I have basically 1 centimeter square surface, so there are about like 10 to power 15 atoms you to talk about. So there are like 10 to power 15 atoms, like the rough idea I'm giving. So it means, so that is basically kind of the monolayer. Monolayer means one atomic thickness, you cover your whole surface. So you see here in this table, if I say, this is a very rough estimate only, giving you some idea. I'm just in column, the left column shows you the chamber pressure, and the right column shows you how much time it takes to form a monolayer. Like if suppose, because the gases or the water vapor, they randomly inside, because of the, they got the energy because of the temperature, because of thermal energy, they randomly hit the surface and they form the monolayer. So just to complete one monolayer, means you complete coverage of your surface, if your vacuum is 10 raised to power minus 4 torr, is very small, 0.02 second. Means your surface is, suppose you are working with some surface, but now your surface is not the virgin surface, it got some kind of monolayer, some contamination layer. So means, so this is going to be contaminate your surface. So what does it mean? If I go to 10 to raised to power minus 9 torr, so theoretically I get like something like 35 minutes or more than that. So if my vacuum is better than that, you see, I can go for maybe hours or so. So means you can just fabricate the device, you can do the processing, and within that time your surface is virgin, it is not contaminated. So this is one of the other reason why you have to use basically the high quality vacuum inside the fabrication process, because you would like to avoid the monolayer formation. Now other thing is basically, you see, which is very important case. So mean free path, pressure, these are the very important parameters when we want to fabricate maybe a device or maybe the contacts. The other thing is the arrival ratio also. So like in case of deposition, so arrival ratio means how many number of molecules are arrived at 1 nanometer per second deposition rate to the molecular impact of residual gases. Means you see, still, if I just say it is 10 raised to power minus 6 torr, if I say my pressure is 10 to raised to power minus 6 torr if I'm high vacuum, or even if I talk about low vacuum, but it doesn't mean that there are no other gas. It is the vacuum. So it's still, you see, 10 raised to power minus 6. So if I just talk about in the layman language, like if at the atmospheric condition, if I have a 760 torr or 1 atmosphere around about that, so there are about 10 raised to power 19 molecules per centimeter cube. So this is something like the molecular number, 10 raised to power 19 molecules. So if you go if you reduce to 10⁻⁻6 torr, then you can think of like still there are very large, huge number of molecules per centimeter cube. So still is the mean free path is big, but still there are chances that your basically the vapor species can get hit by the gas molecule, which are still residual gas, which is inside the chamber. So this we define some kind of arrival ratio here. So the larger the arrival ratio means most of these molecules which are actually coming out from the source of the physical vapor deposition, they are actually reaching the substrate. So that actually means like you can increase your deposition rate, and then you if your arrival ratio is more actually. So for some kind of reactive materials, this can be like very dirty, because reactive materials means like if I'm just talking about titanium, and they can easily get involved with basically the residual oxygen, they can oxidize, and then they can make a dirty film. So that is the another thing. Now, now other thing is basically, suppose now we talk about the vapor pressure also. So means suppose we want to deposit some material, and then the idea is like, so means like it is changing from it's changing its state from solid to, maybe if it is sublimating, it is changing from solid to gas phase or vapor phase, or if it is maybe from the melt, then it is changing from solid to liquid, and from liquid to vapor actually. So the vapor pressure is very, very important, because vapor pressure will define ultimately basically how much is vapor pressure will define basically how much is the deposition rate. So normally you see the vapor pressure, if your operating pressure is like so you depends, like if this is a PT diagram here. So for a given PT diagram, your triple point is fixed. So if I reduce my operating pressure, then basically the surface operation will take place much more easily. So you can see in PT diagram, I can change basically the operating pressure, and that can change my basically the triple point. So I can basically, you can go for the easily you can increase the vapor pressure. You can easily go from the melt state or solid state to the vapor phase state. This one can do by using basically this Clausius-Clapeyron equation. I'm not going in very much detail, but that is the idea. So this is basically, here you see in this this graph is showing basically the vapor pressure versus temperature. So the vapor pressure is also a function of temperature also. So depending on different temperatures, the different materials have the different vapor pressure. So vapor pressure means, suppose you want the vapor pressure, like because you want to increase the vapor pressure. If I want to suppose deposit aluminum, then you want to increase its vapor pressure. So that this will give you the idea basically at what temperature, what is the vapor pressure. So so you normally we have this kind of a experimental graph with us. Then what you can do, we have this kind of graph, then we can use like a Knudsen model for evaporation here, where we can just calculate the mass evaporation rate. What is the mass evaporation rate? So that is actually the function of temperature, that is the mass, the function of the molecular weight of the species, and also it is the vapor pressure. You see, it is the function of vapor pressure of basically that liquid or melt, and the vapor pressure, and then you have to subtract the vapor pressure of the partial pressure of the vapor in the gas. So basically it's proportional to your vapor pressure of the liquid actually. So more the vapor pressure, that means like the higher the deposition rate. So for example, so we have this kind of a model, and then you can just for different maybe different material, you can just, like I have shown you, we know basically the vapor pressure temperature dependence, then you can just put basically this vapor pressure there, and you can obtain, like we have this just example is for aluminum, you can calculate basically what is the mass evaporation rate. Now, now the deposition rate here I'm just talking about. There can be two types of sources here. So the deposition sources, like it can be a point source, or it can be a surface source. So point source means like I have maybe some deposition source where the vapor flux can go in all the direction in isotropically. Means you can just see there, like I have a point source, and vapor flux is coming out from this point equally in all the direction, And then we can calculate basically applying a little bit theory here. You can calculate, because if I have maybe easily you can do that. You can apply basically, you can calculate how much is the per unit area. You can define the area vector, then how much basically the vapor flux is going from there. And then you can calculate basically, and we can also calculate the deposition rate also, how much deposition rate is there. Suppose you have a substrate here. Now, if I have a surface source, we don't have the point source. If I have a surface source, then basically you see, because it's a surface source, then you don't have the isotropic deposition. The deposition is basically only in the, you see in the cos square 5 kind of like cos square kind of a function here there. So this will be actually, so there are two types of sources here. So depending on basically the type of source, the deposition rate can be calculated very easily. Is theoretically we can calculate some idea, we can get how much is the deposition rate. Now, so so I'm just giving you the example here. You see, this is the thermal evaporation. So we just talked about the sputtering. We have seen the thermal the magnetron sputtering, where we have the target and the substrate. Here we have a thermal evaporation system. Means you just like in thermal evaporation is very simple technique, where you use some kind of a crucible here or boat, like this kind of boat. Boat is means it's a high resistive material. High resistive material, and also its melting temperature is very, very high. So what happens actually, we pass current from there. It's a high resistive material. So you pass a current in the boat. So this because this resistance is very high, so it get like heated because of I square R. So it get heated up. So this boat get heated up to very high temperature. You can heat up to 1200 to 1300 degrees centigrade, and then we put basically our material which you want to deposit. So this particular boat is made of some special material, so that like suppose if you want a gold here, so you put the gold wire here, gold pellet inside that, or so that actually like when you heat, the gold actually get melted out, and then from gold melt we just create the gold vapors, which is actually inside the chamber, and then it get deposited there. So the one of the property of this basically the boat material will be that should not interact with your evaporant material. So that's why mostly we use the boat material, which is basically refractory material, which we call which is not making any reaction with the gold, like tantalum. We can use tantalum, tungsten. These are the material normally which are sometimes graphite boat also people are using. So these are the boat which you, and then it can be of different geometry also depending on your source. Like if I have maybe like a wire kind of thing, then we can use maybe this kind of geometry, or if we can use a crucible put, and then your like the resistive wire will heat the crucible and the material can deposit, or mostly most of the technique we use the boat kind of geometry. So this is a very small area which is open. So it's a surface deposition, like like it's not a point source, like, but so it's like having a kind of a width. And the common evaporant material which we use for thermal evaporation is gold, silver, aluminum, tin, chromium. This we normally use. And but the like I can show you basically the picture here. So you use like when this is one of the operator which we have in our clean room. So you can see here basically that these are multiple crucible here. So you can and there is a win, like I say, there is a window here which you can just a shutter which you can just put there when you don't want basically material to get deposited. This is my substrate here, and which is cooled by water. Substrate is cooled by water, and there is a like thin film measurement setup which we call quartz crystal, which by which we measure the thickness of the film also. So what happens actually, you see, you just heat this material inside that, and then it get evaporated and get deposited on the material. And then when you just check basically the thickness, when you get the right thickness, you put the shutter and you turn off basically the evaporator. Now, one of the problem, if you see, if I just take the, in case of E-beam, instead of, I am not showing the picture, but in case of E-beam, you have some kind of crucible here, and the electron beam is actually hitting the surface, not like the, so one of the advantage of E-beam over the thermal evaporation is that in this case, actually, this whole geometry is get heated up. So this whole boat is heating up. So your boat is also heating up. Your material is also getting melt because of that. In case of E-beam, so you can just, because the electron beam, very kind of dense electron beam, you can basically, you can shine, you can on the surface, you can localize that. So you can get a localized heating. So your chamber or your other material doesn't get heated up. So the contamination issue is less in case of electron beam deposition. But the other advantage of thermal evaporator is it is like simple, cheap, and also it's very easy to do that. You don't have many parameters here. So that is also for maybe for in case of our clean room, like for device fabrication, for normal the metallization process, normally the thermal evaporator is good enough. So this is just a picture of that. You can see here that we have thermal evaporator. I'm just showing you only few facilities. So this is where you use different, and these are like the vacuum like control units. These two chambers are there, and where you insert basically inside the material. So so that is basically about that actually. Now yeah, so this is like I'm just showing you the evaporator which we have. So this is a local evaporator which we design and then we get fabricated by this company. But so now I just end here, and then really thanks for your attention. And then I just see if there are queries, then I'll be happy to answer those. Yes, thank you.
Thank you very
Thank you
much,
so
sir,
much.
for such a comprehensive and technically enriching session. Your explanation of cleanroom practices and nanoscale fabrication environments was extremely insightful.
Yeah, thank you so much, sir,
This
for taking out time and sharing insights with our participants. So, participants are requested to share questions through the chat box, or we will be happy if you can raise your hand so that we can interact with sir.
Yeah, I can see one hand, but it's muted. So I don't know, like we allow or
Yeah,
maybe like.
yeah, I have shared the rights with. Sir. I think Ramachandra sir, is it you? Okay. Let me just check the chat box.
ma'am, there's one question in the chat box.
Yeah, we can probably take that.
What ways contaminations in clean room can be cleared quickly?
So, sir, we
Yeah,
have
so
one question.
yeah. So the question is regarding the probably the way how to, like how fast we can, or like what is the, can you just somehow I missed that. Can you just
What ways contaminations in clean room can be cleared quickly? That's the question, sir.
yeah, so in the clean room, actually, there are different kinds of basically technology. So like there are in like different clean rooms. So our clean room, which we have basically is basically the floor where which actually which get which where we have used basically the airflow system. And normally quickly like how quickly we can go, we that's not the that's why we try to avoid basically the contamination. So the rate of like the basically the airflow is controlled. So it is not, we don't normally we don't change it, but we use basically the HEPA, like in the clean room, the HEPA filters are normally used. So HEPA filters are there. So you have, I can see like there are plenty, like a lot of HEPA filters, and so also the design of the clean room in such a way that the airflow is a positive pressure. So in clean room, the pressure is positive actually. So pressure is positive, so that actually whatever is actually inside the in the room, the pressure is positive. So the gas actually moves from the room to the outside. So that is one of the thing. So which has to be maintained throughout. So but it will like take time also. So there is a like the in the aerodynamics there is the flow. So we cannot actually change that actually. So it is there. So once it is contaminated, it will go by its own actually. But the important thing is there is a positive pressure which is inside the clean room, not like in our home. So it's like little bit positive pressure so that the air flows out from the room to the outward. Yeah, through the HEPA filters. That's the idea.
And
I
so
have
there's one.
enabled your mic, Nagaraja sir. So there is one.
Yes, sir. I have one question.
Yeah,
Yes.
you are. Yeah,
Sir, am I audible,
yeah,
sir?
please.
Sir, when we are depositing the material onto the substrate, so what are the means basic criteria to choose the substrate? Means what kind of substrate has to be chosen to deposit the material?
Okay. Normally, basically, it is basically in the reverse way. Normally, basically, suppose you want to make some ohmic contact. So for the ohmic contact, like if I'm making a ohmic contact with either with silicon, like you will be knowing like what type of device you are making. Suppose you are making device with high band gap, large band gap material. Suppose which is zinc gallium oxide, or it is indium phosphate, or if it is silicon. What type of device you want to fabricate? So it is like silicon device. Then you want to make some ohmic contact or Schottky contact. So if you want to make a ohmic or Schottky contact, you have to basically check its work function, and then basically depending on the work function, then you have to know basically you must know what type of work function you have to select for the ohmic or Schottky contact. Then the metals also you have to basically check on that basis. So mostly that's why you see mostly when we talk about the ohmic contact, we always go for alloy. You always go for the alloy because the problem is most of the metals when they in contact with the semiconductor, they form Schottky contact. So that is the one of the like problems. So we go by the alloy, and then also it depends basically. So basically the metal deposition depends on basically what you want to do. You want to basically make metallization, you want to make ohmic contact, Schottky contact, or you want to make a film. So basically the selection of the material depends on your what you want to do, and also what is your substrate. Means what is your substrate? Is the semiconductor silicon, or if it is going to be a large band gap semiconductor. So depending on that, so it's like work function is very important there. Yeah.
One more question we can take.
Uh, there is one question in the chat box as well.
First, we take from Ramesh Babu sir. Sir, I have enabled your mic. Okay. Sure, you can read from the chat box.
Okay, ma'am. Uh, so there's this question. Can you overview on how to characterize the thin films deposited on semiconducting and metallic films?
Okay, so yeah, so you are actually asking about basically how we can characterize the thin films. So now, see, the characterization of the thin film depends on basically the thickness of the film also. So like if you want like a conventional film, suppose if I am just depositing some film which is 500 nanometer more than that thickness, then basically it depends like what type of like what you want to know about the film. Suppose the type of characterization is like structural characterization. First thing is the structural characterization. You want to know basically what is the material, what is the face of the material. Suppose you are depositing silicon, so you want to know basically if it is a single crystalline silicon or there is a silicon dioxide layer on top of that. So one idea you can do basically you can do the XRD, X-ray diffraction, which is the simplest technique. You can get from the idea from there. Then you can do the morphology like you if I suppose morphology means how the surface looks like, what is the roughness. So you can do atomic force microscopy or scanning electron microscopy. That will give you basically the microscopy. This microscopy will give you basically the morphological information. You can also do the chemical information. Like chemical information means, suppose if I have suppose I have a zinc oxide material, and I want to know basically what is the suppose what is the chemical information, how much zinc is there, how much oxygen is there. You can do basically the EDAX, so you can get basically the chemical information from there, or you can do the X-ray photoelectron spectroscopy also. That will give you basically the idea about the chemical. So you can get the structural information by doing the, in HR term, the diffraction techniques, or by the XRD. Diffraction techniques will give you mainly the structural information. Microscopy, either type of microscopy, scanning electron microscopy or atomic force microscopy will give you the morphology, or the spectroscopy, any kind, like if I just talk about the spectroscopy, can give you basically the Raman spectroscopy or basically the photoluminescence spectroscopy. This will give you basically the material information, like chemical information. So these are the techniques one can do, but you have to be very, very careful. Like if suppose your device is of the nano size, then you cannot do that. Like suppose if I have a single nano wire, gold nano wire, which is lying on the silicon substrate, and you are doing basically the X-ray diffraction, then because your size of nano wire is only suppose 100 nanometer and 10 nanometer, so X-ray, the spot size of the X-ray is very large, and basically the information is coming from deep inside, like in micrometer depth. So your spectra will only show only the silicon. You won't get any basically the gold. So for those small structures, your technique should have the resolution also. So when we are actually measuring the doing the characterization, we have to be very, very careful about what is the volume or what is the area we want to characterize. So you have your characterization technique has to be of that same order. Like I can use the HR term, high resolution transmission electron microscope, to characterize basically my gold nanowire which is lying on the silicon substrate, or maybe atomic force microscope or scanning tunneling microscope where you have very high resolution. So this is also one of the parameters people have to, researcher has to be taken into account while characterizing the film.
Thank you so much, sir. All the participants are sharing their thanks and regards with you. And on behalf of all the organizers and our Department of Multidisciplinary Engineering, we are really thankful for your continued support to all our programs.
Yeah, thank you. Thank you for attention for all the participants also. Yeah, thank you.
Thank you, sir. So I request Kashvi and Shivam to please take it forward.
We kindly request all participants to take a moment to fill out the feedback form for technical session 3.
So
The
with
feedback
this,
link has been shared in the chat box. Your inputs are extremely valuable to us and will help us enhance the quality of future ATAL FDP sessions.
So with this, we are coming to the end of technical session 3, and we will take a short break and we'll start with our next session, which is by Professor V.V. Rao. He's already inside the meeting.
Okay, thank you.
Thank you, sir. Thank you so
Okay.
much. Yeah. Thank you, sir.
Goodbye.
Bye, sir. Thank you. Evening, sir. Can you hear me?
Yes. Hello.
Yes, sir.
Can you hear me? Anu, how are
Sir.
you?
Yes,
How are
I'm
you?
fine, sir. How are you?
Fine, fine. How is Shivam? How are you?
Sir, I'm fine, sir. Good evening, sir.
Uh, so, Madam Lokesh, all are fine?
Yeah, everybody, sir.
Okay.
Yes. So, our entire
Great, great.
department is actually attending and with us.
Great.
Yeah, thank you, sir.
And
So,
maybe you can just check whether my slides are on or
yes.
whenever
Yes.
because I'm little old and I get confused when I have to share the screen. So That's why I requested her. I think you know that you are supposed to change the slide whenever I say next slide, please. I will
Yeah,
tell,
sure, sir.
please.
Yeah, we will take care of that. So I request
Yeah,
the coordinators to please share the
yeah.
slides.
Just check whether slides are there
Yes. Please first share and we can check and then we will start.
so that we don't lose time.
Yeah.
Is the screen visible?
Yeah, it's visible.
Great.
So, Kashvi, I request you to please start uh, with the session and introduce sir to all our participants. Sir, can we start?
Yeah, it's up to actually participants may get little tired maybe, but of course, if you start early, they will also go home early.
Yes, sir. Yes, sir.
Yes.
Sure. So,
Okay.
you may please start, Kashvi and Shiva.
We now welcome our second speaker for the day, Professor V.V. Rao, a distinguished expert in vacuum cryogenic and semiconductor technologies.
Professor Rao obtained his PhD in physics from the Indian Institute of Technology, Madras, served at IIT Kharagpur for 40 years, retiring as professor from the Cryogenic Engineering Center, and has recently joined as University Research Advisor at Sri Venkateswar University, Tirupati, after completing his tenure as visiting professor at IIT Tirupati. Professor Rao's research spans vacuum technology, semiconductor engineering, quantum computing, cryogenic engineering, superconductivity, and advanced materials, and he has received advanced training in Germany and France in vacuum and cryogenic technologies.
He is a Fellow of the Indian Cryogenics Council, Senior Member of IEEE, Life Member of the Indian Vacuum Society, has published over 110 research papers, guided multiple PhD and postgraduate theses, authored a book on vacuum science and technology, delivered an NPTEL course, and organized 45 short-term courses. We now invite Professor V.V. Rao to kindly begin Technical Session 4 on Vacuum Technology for Semiconductor Fabrication. The chat box will remain open and Q&A will be taken at the end. With this, I extend a warm welcome and over to you, sir.
Thank you. Thank you very much. I am audible and visible.
Yes, sir.
Yes, sir.
Yeah. Of course, if you are having vacuum, you cannot hear what others are talking. Okay. And now, it's already 1.5 day passed. People have been exposed to different processes, different technologies involved in semiconductor manufacturing. It is a very important discipline realized by our government of India, and North Cab University is doing a really good job to bring it to the masses and public, and that way they regularly organize, and I'm very happy about it. Okay. Now, as I already introduced me, I don't want to say much about the topic because as we go ahead, we'll understand that. But one thing I wanted to tell is uh, vacuum is basically in Latin, it is nothing. That is the English word. Just like English word, in the Latin, it is called nothing. But unfortunately or fortunately, it is everything for us. All those 214 people who are listening to me, if they are sometime or other has to face a, some sort of process, even tangentially related to semiconductor manufacturing, they will inevitably come across a word called vacuum. Because without vacuum, neither lithography works, nor ion beam etching works, nor implantation works, nor doping works, nor even analysis of what you have done like SEM, TEM, they don't work. And deposition and finally metallization as well as the cleaning processes And finally, when you package from A to Z, next slide, please. From A to Z, every process requires vacuum technology. So why I stopped from A to Z is, if I suddenly say A to Z, it has no meaning. Here you can see. I'm not going to discuss semiconductor aspect of it because already it has been discussed. Even I'm happy the speaker just before me also has discussed about various processes like clean room and also what goes on inside, deposition methods like sputtering, etc. That makes my life easy. And by now you all know that semiconductor chip is a very, very important piece of information because all of you are looking at this TV because of IC chip. All of you are having cell phone because of IC chip. All of you are having TV because of IC chip. All of you are having bank accounts or phone pay, everything without actually physically going there because of communication technology based on IC chips. Okay. So the figure shows chips on the right side and the left side. In the bottommost figure, if you see, right side, the fabricated chip is there with the necessary pins for controls, etc. And the left side, you have a silicon wafer, simply like a puppet. From there, we have to bring up to this. So in that wafer, we try to deposit several small diced blocks, which are called dies, and each die has got a deposited and controlled electronic circuit, and each die is called a chip, and that will be there in one of your cell phones or TV or etc. I don't have to tell all these things. You know much better than me because you have been working in these lines. So basically, the manufacturing of semiconductors has got several complex processes. But you experts, you should not think it is a complex. Several clean processes, green processes, neat processes, high-tech processes. Because it is complex with respect to layman, but for scientists and engineers, they are basically high-tech processes. So all of you must have done B.Tech, M.Tech, but now this is a high-tech, okay? So there are 150 different steps are there to bring the silicon wafer into a fine chip. And there are millions of components inside and all that. If I keep talking, it will go on, and I don't want to talk because today my speech is not on semiconductor chip manufacturing, but it is vacuum technology for semiconductor manufacturing. Because if everybody speaks about semiconductor manufacturing, you will get bored. Already you have been exposed to it, and tomorrow onwards you have series of lectures again. So you will be bombarded with lots of high-tech talks on lithography. Already yesterday there was a beautiful lecture on lithography, etching, etc. Today also clean room technologies are there and superconducting, and then very soon you are going to have different other technologies like metrology, how to measure that fine things and how do you test it. All these things are going to be exposed anyway. I don't want to repeat the same thing here, but you may not be able to get a feel of the ambience that is required for making these things called vacuum technology. So that also, if you know, then you can say, I know the software, I know the hardware, I know the instrumentation, I know the materials, I know the depositions, I know the electronics. You can feel like that, okay? And with a little bit of knowledge of electronic circuits, etc., you will, some of you, if you are not employed, you can easily get employment because there are going to be lots of companies manufacturing chips, but around the chip there is a lot of ecosystems, high purity gases and materials, wafers, and even to make wafer from the sand to the wafer, that silicon is basically from the silicon dioxide, which is the sand in our beaches. So if only you can remove the oxygen, your Marina Beach becomes a Silicon Valley, but which is very tough. So, okay, so normally there are different processes like chemical and thermal processes to make ingots and then crystals and then a long crystal of 10 meter to 4 meter tall and half a meter diameter or a 20-30 centimeter type. And then it is pulled by a crystallographic technique. All these are going on under a clean and green vacuum envelopes. Okay, so vacuum is not only necessary in chip manufacturing of a semiconductor circuits, it is also necessary even to make the base, the silicon wafer. Yesterday he was talking 90% of the silicon wafer is only support, but it is a single crystal, very costly piece, because if you make it too thin, it will crack. Okay, so this single crystalline silicon wafer itself is manufactured under vacuum technology. That way, if you take the zero end, that is this wafer, production also requires vacuum technology. Whether you have produced or not, if you want to measure something, you have to use scanning electron microscopy, transmission electron microscopy, ADAX, X-rays. Every piece of this X-ray equipment or ADAX, they are all operated for their own principles of operation. They require vacuum again. So vacuum is required for manufacturing semiconducting chips, for manufacturing semiconductors, for manufacturing wafers, for confirming the structures, for chemically analyzing the processes and controlling the processes by a long mean free path, like whether it is ions production or anything. In fact, for the sake of information, you can say you cannot have ions without vacuum even. If you want to have ion, you have to put an electron, bombard it to an atom, produce an ion, accelerate it so that you will get a high velocity ion or electron. You can use electrons also with high velocity in scanning electron microscopy, or you can use them in electron beam lithography, or you can electron beam etching or heat treatment, etc. You can also use ions to make ion beam etching or ion beam depositions, even ion implantations, or even ion cleaning. So all whatever tools are also require vacuums, and the controls require vacuums. The actual processes of various 150 processes, they are called front-end process and back-end process. Front-end is up to the transistor manufacturing, PA, that is CMOS type of transistor manufacturing and gates, etc. And then back-end is to assemble them and take the necessary contacts and metallization and finally bringing the packaging aspect of it. There is a small overlap between those two processes, and almost all these processes require vacuum technology. So I would say by now you already know, and if you do not know, just take it for granted. Get used to these words: the front-end process, back-end process, fab, and wafer, and then testing and packaging, and then etching, photolithography. All this is because we want to make lakhs and lakhs of transistors, resistors, capacitors in a small 1 square millimeter area. So that's why you require highly controlled nanoscale structures. And those controlled pieces should not be chemically different from what we want. So it's a huge high-tech precision atomic level engineering, which is possible because of vacuum technology. Whether it is doping or a deposition or a dry etch or a lithography, they require different levels of vacuum. That's a different story, but they require vacuum. And what is this vacuum and why it is required? By now you already know in the semiconductor manufacturing. But unlike semiconductor manufacturing or electronics, vacuum technology is also necessary for several other technologies. Today, all the metallurgy, high-tech metallurgy is going on with vacuum technology. Okay, and I also say that all the particle accelerators, the entire BARC is the costliest customer of vacuum technology. Entire ISRO mission, once you cross 10 kilometers, millions of kilometers, it is under vacuum space. So they require a lot of vacuum technology in space simulation chambers. And you require vacuum for day-to-day life, for even making high-tech drugs, and even the coffee powder that you are taking. Everywhere you require. The processes involved in these mundane processes like food and pharma are same in semiconductor high-tech processes or space or nuclear. Because everywhere it is the chemistry, it is the physics and the controls. Okay. So here in coming to the semiconductor manufacturing, we do the depositions, we do the etchings, we do the drying process, we do cleaning process. All that of course has to be done in another clean room called clean room technology, but that is at atmospheric conditions. But if there is a dust or something, if it goes through unavoidable leaks through the vacuum chamber, that dust will be there. So it is a combination of several technologies have to be mastered. It's not difficult. Somehow over 30, 40 years, we are concentrating on software, not hardware. So we lost the bus, but we have realized now. So we are starting from scratch the semiconductor manufacturing. Okay. So I wanted to get convinced that vacuum technology is the enabling technology for all the processes involved in semiconductor manufacturing, whether it's a front-end process or a back-end process. Next slide, please. And of course, you will have different levels of vacuum for different processes. But what are these various processes I have listed here? And well, if I want to talk about it, each paragraph will take 2 hours because we teach this subject over a period of 6 months to our BTech boys and MTech boys, semiconductor manufacturing. So I cannot cover a particular aspect of background aspect of vacuum technology in 1.5 hours unless I skip some of these materials research oriented things. But still, I want to touch upon some of the processes so that you get used to it. This is an interrelated subject. And basically processes like deposition, physical vapor deposition, or chemical vapor depositions, or low pressure plasma depositions, or atomic layer depositions. All these processes require high vacuum chambers in which the clean things are going on. And not only clean, controlled. Just now in the earlier talk they were discussing, the mean free path concept he has introduced, so I don't have to talk more again. As you increase the vacuum levels, the distance between two collisions of the ambient molecules will keep on increasing. By the time we go to 10 to the power of minus 6 star, which is nothing compared to the ultra high vacuum required for semiconductor manufacturing, it is already the mean free path is kilometers, hundreds of meters, and the actual gap between the substrate, which is our semiconducting thin wafer, and the bottom material, which is the evaporating material, etc., like a semiconducting material. These things are only 30-40 centimeters in our 1 meter. So naturally, no other interaction takes place excepting what we want, such depositing silicon or silicon dioxide or etching or some other thing. Only those molecules can travel straight line path without hitting with each other because mean free path has been made artificially much longer. So most of them will travel from the source of the cause, whether it's a thermal evaporation or a sputtering, and then it goes straight to the piece where it forms certain materials, and you dope it, it becomes P-type or N-type, and you make the couple them, you become PN junctions, and then there several such PN junctions will make multivibrators, several such multivibrators will make logic gates, several logic gates with various other things like flip-flops and various other mechanisms like switching circuits. It will make the CPU, and from there with the motherboard you will get the computer. Okay, so the starting point is the two-dimensional deposition, and then cutting them using VLSI technology to make almost zero-dimensional dots, and then dope it, and then metallize it, and then package it, and finally take a small speck of that dye, putting it into a little relatively large looking chip. But all other thing, 99% of this is only plastic and other things. The basic main circuit is very small, but it has to be handled very nicely. That's why it is called packaging. That requires, that's called handling of the dye, and all these things are going on under vacuum. And there will be different chambers, one for lithography, one for etching, one for deposition, like that. So the same silicon wafer We'll go at various places, get various things. The way we go for buffet dinner, we go here, we take that, we take this, and then finally sandwich it and eat. So same thing here. So different chambers like dielectric etching or conductors or polysilicon etching or ion implantation, all are vacuum based. And when you want to dope something, that called impurities, but impurities in ppm level. So that those materials in ppm level, if you have to be deposited in a gas phase and going into the solid state diffusion, they should not interact with other atoms. So the space must be ultra high vacuum. So the need for vacuum, by now you must have got a feel of it, but I might be missing a lot of points because of lack of time, because I have to introduce some vacuum technology also to you so that you are officially knowing the mechanical and electromechanical aspects of semiconductor manufacturing called vacuum technology. If you want, I will just give maybe every slide, because if I keep on talking, you get little bored. I want to give you maybe 1 minute to read this slide. So I have explained already, but I wanted to give 1 minute. You please go through it, just read it by yourself. I'll come back after 1 minute so that I also get rest. 1 minute only, exactly 1 minute. Just read it. And it's worth. Okay, your time is up. Next slide, please. So basically, what I wanted to impress on is there are so many processes going on in a clean room, and you can see those clean rooms right here in the bottom. And that's how a typical clean room facility of a semiconductor manufacturing, having several pieces of equipment called tools, one for etching, one for lithography, one for this, one for that, like that. And the wafers are going on the top, goes to various places. You see on the top ceiling of that, in the figure, that will go everywhere. And entire space should be very clean. The cleanliness can be obtained in a clean room, even at atmospheric pressure, with a lot of money. Or if you put in a vacuum, without much money, you can get the same cleanliness. But you cannot get, you have to use both, because without clean room, people will not be there to operate. Unless there is a robots, you cannot make a vacuum room and then vacuum chambers and then vacuum depositions, etc. But maybe after future, after 30, 40 years, there can be vacuum robots. You don't require anything. Then requirement of clean room also may go down. Okay. So we'll have to see all that, how world is going on. Like that. So ultra pure gases for deposition, doping, purging, they all have to be done under leak tight piping everywhere. Because if there are leaks, what is dopant impurity becomes an impurity on metallization. When you are metallizing, making the contacts, that time also it's a thin film, nanoscale, but that fellow is supposed to be copper or silver. But when you are doping, it is phosphorus or boron. So different times, different things are happening on the chip. Chip contains millions of dies. Sorry, not even million, maybe thousands of dies, but each die will have thousands of circuits. That way you will have millions of components in one 30 centimeter chip. So you deposit everything to maximize the throughput. You do all those things parallel processing. Otherwise, you can't deposit one by one, one by one. So there are, over a period of time, over last 40, 50 years, technology has developed like anything. So today we are doing uniformly on a big wafer. But later we cut that wafer into thousands of small dies, and each die will be there in one of the chips basically. Chip is only containing 1 by 10,000th of that area of that 30 centimeter die. See, most of you know all these things, but I am thinking there may be some student, there may be some people who are first time hearing this. That's the reason I'm talking in a base language. Okay. So in the just like we have vacuum equipment for the actual processes, we also require clean rooms, and we also require that XYZ tilt rotation type of processes, and very controlled way the wafers are traveling from here, and they enter into one relatively poor vacuum first and clean everything, and then open a gate wall and go to the real process. You get it done like that, because you, like just now he told, a shower for the man to enter into a clean room, you have to have a shower, then only enter into that. Similarly, chip making, that wafer has to first enter into a chamber, which is a rough vacuum chamber, and then doing some operations of cleaning, etc. Then only it has to enter into fine. Directly from clean room, it cannot enter into ultra high vacuum, because ultra high vacuum, once you expose it to any atmosphere, it will take a lot of time to get vacuum, then only you can make deposition. So you don't want to spoil that ultra high vacuum. You make a rough vacuum surrounding this ultra high vacuum. That is called pre-evacuation, and there are walls, automated walls between them, and all these things are there within that. So this is how it looks like. Multiple tools will be there, the interconnections will be there, and you'll have to have transportation, and it contains all the high-tech equipments which are vacuum-based, like UV lithography, 10 power minus 8 tar, doping minus 4 tar, ion beam implantation minus 7 tar, thin film deposition minus 7 tar, 10 power minus 7 I mean, metallizations, testing, encapsulation at minus 1 tar, so moisture removal at minus 3 tar, cleaning of organic impurities at minus 2 tar, and sometimes chemical vapor depositions, sometimes physical vapor depositions. So this how different pieces are kept within that semiconductor manufacturing chamber facility, which is looking in the left side. That is a typical facility, whether it mostly it is done in Taiwan and other places. Now in India, many industries are taking up this. And right side, how those silicon wafers in a box, they go here and there. All that is shown here. This is not vacuum technology, but I want you to know that the processes are all vacuum related. So again, I'll give half a minute or 1 minute to go through it, and I'll come back, so that you will not miss what I have talked, or you will try to assimilate it little bit. That's why I want to give half a minute or 1 minute. Please go through the writing. If you don't understand, when I say next slide, before that, you can always stop and ask me. No problem. I know it is muted because I am asking you to go through. Just read the lines. That makes you mentally prepared for the next slide. Because if you are not mentally prepared, if I keep on talking, okay, that is just look like a delivery of a lecture. That's all. Okay, so this is somewhat background, and whatever you are seeing, whatever you are seeing there, uh, if you don't think about that room, the rest of it is under vacuum. All that equipments which are called tools. Okay, so and why do you require vacuum now? Next slide, please. Okay. This is exactly what others are going to talk in detail, but I just want you to understand that the central portion, which is very important repeatedly, is called lithography with masking, etc. And there are several other processes which are linked to this, whether it's an implantation or chemical mechanical planarization of the smoothened surface of a deposited layer, or fresh layers of chemical vapor depositions depending on P type or N type or whatever impurities you are depositing, or metallization like physical vapor deposition like metal films, or etching, so that after lithography you need to etch and only certain locations only you want to deposit, other locations it will not get deposited, so that you will get PNP transistors and resistors and attached circuits automatically made, so that you will get nano circuits embedded. And finally, in between etching portion, unwanted things to be removed, and then cleaning now and then diffusing the dopants and waiting for some time till you got your proper implantation of the impurities. Otherwise, you may think that you have made some chip, but the actually P-type, N-type things have not been properly doped. You are not getting that much concentration of the P or N-type or holes or electrons, and they will not behave like a logic gates. So your idea of software 100 or machine language will not work unless that semiconducting circuits operate it exactly like 0 means low voltage, 1 means high voltage. These are all made out of doped semiconducting layers in the form of CMOS, etc. So unless the hardware is perfect, you won't get it. So the photolithography I have shown in the right side in the process flow, there is a thin film technology and there is a design wafer that is called fab design. That's a theoretical. Afterwards, you are entering into hardware, then cleaning, implantation, etching, planarization. At the end, you'll have to test and assembly. If there is something wrong, again go back. So there are multiple directions I have shown. It will take some time for you to understand. It's not that easy. But I just want you to keep it with you. All the slides will be given to you. I request the coordinators to hand over all the slides. They are good enough. And if you want any particular slide to be explained later, you can call me on any Sunday at 11 o'clock. We can discuss. Okay. So please go through it. Again, my standard technology in BTech and IIT also we do the same thing, because otherwise they will be sleeping. So after I tell something or other, every slide, I give 1 minute for them to see. And they can generate doubts, or they can understand, or they can assimilate. It is up to you. So please go through it for 1 minute. And you can, if you feel uneasy to disturb, what you can do is write down the slide number, and then your doubt, just scratch it on your pen, and then at the end we can always bring it back to that slides fast slide mode and all. Okay. Of course, not too much of discussion is possible because of limited time, and we will see how we can go ahead. So these are basically various processes. It is another way of looking at it. But why I am telling all this is under vacuum. Okay. So already time is up now. Next slide, please. So let us go to the what all I have been talking. It's vacuum. What is that? First of all. Well, uh, according to Vacuum Society, already I told you, the vacuum scientific definition is if a cubic centimeter of any space like here contains 2.5 into 10 to the power of 19 molecules, 1 crore times are there, and every cubic centimeter, like a die that we are playing, that much volume contains 2.5 into 10 to the power of 19 molecules. We don't see them. And the gap between them is in micron. Okay. And when you want to go to ultra high vacuum, even in 10 power minus 9 torr, you still have millions of molecules. Because from crores and crores, you will go to millions and millions, lakhs and lakhs. That's all. It's not that vacuum means perfectly atoms free. It's not like that. So Vacuum is defined as any given space having a molecular density less than 2.5 to 10 to the power of 19 molecules. Okay. In fact, only after the vacuum technology was developed, electron was discovered, proton was discovered, ions were manufactured, discharge tubes were made, then only semiconductors came, then only electronics came. Okay, electronics, which is dynamics of electron, is impossible because you cannot get an electron here if all the atoms are neutral. Okay, otherwise we will get shocked. So this vacuum technology is the first thing which you have to track, which you have to handle whenever you are getting a job or whenever you are teaching or whenever you want to do research in semiconductor manufacturing. More than 70 to 80% of the time goes in solving the impurity problem, tightening the flanges, not getting vacuum, control valves are not opening, some electronic circuit is not operating properly, some gases are not flowing properly, flow meters are not working properly. These things are there. This is not a software, it's a hardware. Okay. So this is the idea. So you have to have some basic knowledge of vacuum technology. And left side I have shown a size scale. This is just a mechanical engineer's way of thinking because we teach this subject to our mechanical engineers, chemical engineers, BTechs in IITs, in addition to, because some of our students, even in IIT Kharagpur, the metallurgy student, who has done metallurgy, who has never heard of electronics or anything. Later, he became in the computer, he went to the material science, understood semiconductor manufacturing, etc., etc. Later, he did some other high-tech material science. He has never done computer science or electronics, but for example, just I am talking, he is our proud student, Sundar Pichai. He is our IIT Kharagpur student only, and he is now top boss of Google. So there are several such people who are working in various high-tech places in all over the world who have understood hardware as well as software. Then only they can master these things. If you do not feel that atoms and flanges, solid state, liquid state, after all it is a solid state device, okay, and gaseous things, precursors, chemical vapor deposition, physical, you can't call yourself as a semiconductor manufacturing. You can at the best call yourself as a software. So that's how vacuum is important. I just wanted to link it with all those things. Bear with me for some time because now this sort of short courses are to get a feel of the subject. If you want to really master it, you have to take 1 6 months course on etching and lithography, another 6 months course on deposition technology, thin films, another 6 months course on fab design, 6 months course on vacuum technology and vapor cleaning. And all these things are very involved processes. You cannot understand in half a day or 1 hour. Okay. So 1 atmosphere is 760 torr or 1013 millibar or 1.03 kg per centimeter square. That means if there is a vacuum in one side and outside atmosphere, and every square centimeter 1 kg stone is sitting, that much force is generated. Okay, which is used to stop a train. All that vacuum technology some other day, if time permits, maybe we can discuss. Maybe same North Cap can organize vacuum technology and full 6-day course. We do like that. Then only you can explain those points. So this slide, whatever I have given, you can go through at your leisure. You don't have to go through because it's a 11th class stuff. That 1 mole of gas contains 22.4 liters. But physically you have to feel. Now you are an engineer. For example, my room is 4 meter by 4 meter by 4 meter. If I ask you what is the weight of the air, if I collect all of them and put into a small piece, what is its weight? You may make 10,000% error. Okay. So for that, you'll have to calculate. You have to redo the engineering. You have to understand. For that, you have to use PV is equal to nRT only because vacuum ambience is an ideal ambience. Vacuum clearly satisfies Boyle's law. If you go through the 11th class, 7th chapter in physics, they have written the Boyle's law, the PV is equal to nRT, ideal gas law, not Boyle's law, PV is equal to nRT. Gas law is ideal gas law, is ideally valid at very low pressures called vacuum or very high temperatures. But actual room temperature is not valid. In room temperature, what is the equation? we have to convert this PV is equal to nRT into some additions. You have to use P plus A by V square and V minus B, because you have to take into volume of those millions of molecules occupied by those molecules. They are not available for the motion. So PV is equal to nRT is not valid for that volume which is occupied by the molecules themselves. So all these quantum mechanical other aspects come into picture, kinetic theory of gases. People have worked out so many things, so many scientists have done. So today we are having semiconductor manufacturing. So there is a mechanics, there is a thermodynamics, there is a heat transfer, there is electrodynamics, there is electronics, there is material science, there is a gaseous phase, an interaction. So many things are there under clean conditions called vacuum conditions. Then only it is possible. So even though the gauge that we are measuring is nothing but pressure gauge only, there is nothing called vacuum. Some people make it as a negative pressure. There is nothing called negative. How can there be pressure negative? Whatever is the atmosphere, if we call it as zero, anything more than that is high pressure. But atmosphere itself is a pressure. So we are going 10 to the power of minus 3 tar means 1000 let us take millibar. Millibar and later tar are more or less same. 760 tar, 1013 millibar. So millibar is easy because it is a 1000 type. Number is easy to remember. This is 1000 millibar. That is one bar. Barometer. Bar is atmosphere. Okay. This 1000 millibar has to be taken into 100 millibar, 10 millibar, 1 millibar, 10 power minus 1, not 1, not 1. Then only you will be able to make semiconductor manufacturing ABC. Otherwise, you will not be able to start anything at all. You cannot make any chip in this world unless you reduce this 1000 millibar to 10 to the power of minus 6 millibar. So orders of magnitude it is going down. If it is going up to 10 millibar, it is poor vacuum. But actually 99.99% of the gas has been removed because PV is equal to nRT. 1000 has become 1. So 999% has been removed. But no application has started excepting brakes or vacuum cleaners, etc., mundane applications, or a filtration or a chemical application or pharmaceutical. But real high-tech electronics will start after that 1%. 99.9% if you remove, electronics will not be there. Because we are able to remove 99.999999, we are able to get semiconductor. If you remove some more, you will get space technology. If you remove some more, you will get nuclear technology. So without removing, if you are satisfied up to removing these air molecules, that is evacuating, that's called vacuum technology, by reduction of pressure, by reducing the molecules or by sucking the molecules when you are producing vacuum, if you are removing 99.9%, no high tech has started. Only it is the 0.1%, all the high technology, metallurgy, advanced metallurgy, electronics, space technology, nuclear, molecular distillation, all of them are there. So that's what I want you to imagine the power. And semiconductors come into picture after you make 1000 to 100, 10, 1, 10 power minus 6. As usual, I'll give half a minute for you to go through, or 1 minute. Just go through it. Left side, the pressure gauge principle. If you take this as the zero, then we call it as gauge pressure. But absolute pressure starts from zero. This 1000 millibar is 1000 above the absolute zero. From that zero, zero means 10 power minus infinity. You have 10 power minus 10 like that. That scale is given in the log scale. In vacuum technology, we plot everything pressure in the form of log scale because 1000, 990 already are approaching zero in the graph paper. Unless you make a log scale, 1000, 100, 10, 1, 10 power minus 1, 10 power, you cannot plot. In high pressures, you can use linear scale. This is another thing I want you to understand. Okay, just I'll give you half a minute or 1 minute to go through it. I'll come back. Please go through it. Just half a minute. You get a feel of the terminology involved in that. If you understand these basics, other things, even if you go through, that's enough. There is nothing great I am showing. Just I am trying to, all of you can recollect what you have studied in 11th class and 12th class. I am telling you all electrical and electronics is 12th class physics, and all mechanical and metallurgy and all those things are 11th class physics. Many times we reproduce same concepts again and again with little bit of more mathematics and finer details. This is a fact and I have seen. So please go through your 11th and 12th class books once again and to formulate proper ideas in the depth. So here we have explained few concepts. What are the things? Absolute pressure concept, Boyle's law, ideal gas law validity, and number of molecules, and 22.4 liters, and STP conditions, and the molecular density we have explained, and the units of vacuum we have explained. So these are the points in this slide. Next slide, please. This lecture is on vacuum technology, so I'll have to talk like that. If they had given me a topic of etching or semiconductor layer or packaging, etc., my style is different. But here it is mostly mechanical. So if you are mostly electronics or electrical boys, you may have to understand mechanical aspect. In fact, the real cost of the equipment is only the hardware. Once you understand all this properly, if you are able to get 10⁻⁷ controls, walls, gates, components properly, it is a child's game. That's all. You can make your own chip industry. Okay. And now, what do you mean by understanding vacuum technology? Like any other technology. Any technology involves production. You have to produce something. Whether it is a rice or a vacuum, or whether it is high pressure or a solid or liquid or anything. Production. That is called production engineering. Then what you produce, you must measure. So measurement is very important. Then what you produce and what you measure, based on these things, this very precision manufacturing production, precision manufacturing measurement, then you design something, either a circuit in electronics or a robot or something. That is called design. Based on mathematical principles and physical principles and chemicals required and materials required and the space technology, etc. Then production, measurement, system design. Afterwards, you get into application. You have to understand the application, whether it's sending a rocket or whether it is making a cell phone or a TV or you're making a chair or anything. You have to understand the application, or a transport or a high-speed vehicle or electric vehicle or a battery. The application is very important. So fourth one is the knowledge goes in like that. Production, you have to produce, measure it. That's called quality control. Then system design for a particular application and actually application. These are the 4 steps. But the 5th step is also important if you are an engineer. That is called troubleshooting. If something goes wrong, costly equipment, these are all very costly. A typical 10⁻⁹ tar system for the EUV lithography, which is the state-of-the-art technology to make nanometer type of chips, which are coming in a big way in our industry, semiconductor industry. That is just like a 1 meter cube ultra high vacuum chamber, 2 meter cube with all these associated vacuum, etc. Its cost is more than 10 crores. Why? Because the materials, seals, components, manipulators, walls, substrates, holding heaters, measurements, scanning electron microscopy, all are connected. Unlike other industries, in other industries, what you do, you manufacture something and give it to scanning electron microscopy or X-ray analysis or something. But it is not here. They are all connected to the same chamber. One chamber is scanning electron, other chamber is X-ray. So it goes there and comes back. Is it okay? Then only it will be done. Because there are hundreds of steps in the manufacturing. So you'll have to be careful. So I'm coming back to our vacuum technology now. So why I'm telling now and then going beyond the story is now India requires the overall vision and high tech starting from vacuum technology only. Very important. Okay. So in a compressor, what we do, we take air from, like whenever we go to cycle shop, we take air and then compress it and store it in a buffer vessel. So the output is in a compressor, the process is compressed air. That is the process. So the process is coming in the outlet. The suction, that is inlet, we call inlet, outlet, suction, exhaust. Okay. These are the terminals. Suction is atmosphere, exhaust is the process. Inlet is the atmosphere, exhaust is the process for compressor. For the vacuum pump, it is the reverse. The suction is the process. We are evacuating that air, we are removing. And the exhaust, where we are throwing? To the atmosphere. So atmosphere comes to the right side and the process comes to the left side. This is what I want you to appreciate. A typical vacuum pump looks like that, and typical compressor also looks like. Both of them I have taken from the commercial pictures. So source and sink changes. For a compressor, source is atmosphere, sink is the process. Flow is always with respect to the 1 bar atmospheric pressure. Our gauges are more than 1 bar. So more than atmosphere, we talk about gauge pressures. But in vacuum, it is a less than 1 bar. Okay, so the flow is referred in the actual conditions. It may not be gas flow. It may be ideal gas, but it may not be always flows. There may be molecules flow. Even the pumps are called turbomolecular pump. They are not called gas pumps. So source is the process, vacuum process, evacuation. That process is called evacuation. And in a closed chamber, if you open chamber, you will never get vacuum. Okay, you have to throttle the gas flows in a sputtering or electron beam deposition or doping. You are only passing few small amounts of gases in the parts per million type of things, or little bit more if it is a chemical vapor depositions. But there also partial vacuum is created. Otherwise, you get mixed up in the gas phase reactions take place instead of taking reactions on the silicon vapor. Okay, so mean free paths have to be adjusted. The molecules from the gas source cylinders through a throttling regulators, when they enter into vacuum chamber, immediately molecules are spread out and they go directly, depending on whether they are in atomic state or ionic state, in the travel path, straight paths, etc., mean free path, all that comes into picture, and they get deposited as thin films. One thin two-dimensional structure, afterwards one-dimensional, afterwards zero-dimensional. Then only you will have micro miniaturized circuit. So this is called the comparison of high pressure and the vacuum technology. Next slide, please. So a typical system will look like this. How much time I have? Because I am almost in the middle. Depending on that, I'll go through.
Sir, we have
Meanwhile,
time.
keep on seeing the figures.
Sir, we have enough
Do you
time.
have?
We can-
Huh?
Yes, definitely.
I have 45 minutes.
Yeah, sure. Sir.
Okay. Anyway, those people who may not be directly interested in these things, they need not worry. But if you are interested in semiconductor manufacturing, which is the focal theme of this conference, you have to know the vacuum technology, because without producing vacuum, game will not start. Okay. So we have to be very important, not only in understanding typical vacuum systems, you should also understand troubleshooting of those vacuum systems. Otherwise, you will not be employed. If you only purchase and then operate, they are called operators. They are not called engineers. Engineers should be able to repair it or design it or optimize it, minimize the cost, maximize the throughput. That means amount of output that is coming. That's where the intelligence lies. Okay, that's where you have to use your math, physics, chemistry, material science, computer programming, and management skills. Very important. I repeat again. Okay, your fundamental knowledge, math, physics, chemistry, with mechanical, electrical, sometimes civil when it is coming to the clean rooms, and electronics and microelectronics is very important in semiconductor manufacturing. And these nowadays, because we are not somehow used to this hardware, everything looks little scary. But actually, those people who have made, they are not having more brain than us. They manufacture everything. Finally, output nicely. They put some plastic, nice looking things. It looks very neat and clean and for polishing, finishing. But actual principles or even in the first those who have discovered an electron, photon and all, the type of pumps they have used are very dirty. The way they have used the fellow Pirani, who has made the vacuum gauge nowadays nice looking many companies make. The Pirani himself has made one to only some 100 rupees, one safety pin type, one small filament, etc. So the discoverers have made it in a very small scale. But when you go to the production for the public use, because everybody requires a cell phone or laptop, naturally the way you do is more of a what you call production engineering rather than the basic science. Okay. Now, a typical vacuum system is shown here. Is a chamber. It's a schematic picture. And the gauge means it measures the level of vacuum. I don't know whether my cursor is showing there. I am showing here, but anyway, gauge is written there. And then air admittance wall. Sometimes you have to admit. If you do not admit, after making all the experiment is over, thin film, all the thousands of depositions have been over. Now chips have been made. I have to take it out for giving it to the packaging or something. How do you open it? Every square centimeter 1 kg stone is sitting because the other side is vacuum. And a typical bell jar of 1 meter square, so maybe 5-6 square meter surface area of 2-3 meter cube volume. Some elephants are sitting on it, 10 elephants. So you cannot open it. Okay. So it is very tough. So you'll have to admit. And initially you have to evacuate it not by high-tech pumps like turbomolecular pumps. You have to evacuate by a roughing pump. So that line is called roughing line. The valve that is connected in between roughing line and the chamber is called roughing valve. Very fast I am explaining the terminology. Some other time you take a full-fledged book on vacuum technology, then or you can go through the 60 lecture series I have given, my NPTEL lectures, which the link I am showing you to the last slide. You can go through it, or otherwise you can say, yes, so vacuum technology and process application, you will get all that. Slowly you can learn at your leisure also. It is available. There are very good books available, very cheap books are available. I have also written a very cheap book, only 120 rupees, I think, long back, some 30 years back. Now I am revising it as a process application. Because that time nobody was asking semiconductor manufacturing. We never bothered. But today everybody is asking. But these semiconductors have been manufactured 40 years back, 35 years, 40 years back. So we made a mistake at that time. So now we are paying for it. Okay. So we'll have to be very careful. So every day lakhs of cell phones have to be manufactured, display systems. There are so many companies which are imported, foreign companies trying to help us also in Bangalore, like Applied Materials is there, Lam series is there, and so many people. But we ourselves have not manufactured. Now only we are starting manufacturing. The government of India is also giving a lot of importance to it, and several state governments are also involved in it. And there is a lot of job coming in semiconductor manufacturing. In fact, that is the reason the North Cab is trying to make these courses. So you'll have to think like that. So right side you have shown leak detectors and residual gas analyzers. These are troubleshooting equipment. For example, you have made PNP transistor. There is a building block of a bistable multivibrator, which two stable states called 0 and 1 state. Several such things are added to make a chip. That's all. So that doping, if it is not proper, this entire circuits will not work. And some millions of such circuits are there. And all of them will be junk in one process. Because each wafer contains millions of components. And next wafer. Every day, thousands of wafers are processed. So imagine the high-tech control systems which are required, the robotics, the electrical controls, electronic processes, and the atomic level precision. These are all very important. So you require a roughing vacuum by a rotary vacuum pump, which is in the bottom, and then close that valve and make this rotary pump to help the high vacuum pump, which is called turbomolecular pump now. This turbomolecular pump should also be initially evacuated by the rotary pump before it is getting ready, because the high vacuum pump is basically a chamber. That's also some mechanical fellow. That has to be evacuated by a rotary pump. So you keep that's called roughing the pump itself. You'll have to rough the chamber. Both of them are brought to the ultimate vacuum possible by a mechanical vacuum pump called rotary vane pump. Nowadays, for cleanliness operations, recently there are other pumps which I will show you. So there are dry pumps which are coming in a big way, but they are not fully developed. You can take up any development of any such pump, you will have millions of rupees, I'm telling you, if you make a high-tech pumps. Most of these pumps are imported. So this is where the technology lies. So you have a high vacuum pump, which is called turbomolecular pump. And this high vacuum pump is separated from the chamber by a high vacuum valve, which is a bigger valve. And why it is bigger and why it is smaller? Because density is more at higher pressures relatively. Poor vacuum, density is more, and less vacuum, very high vacuum, that's called. Vacuum high means pressure is low. People should make sometimes mistake. Very low vacuum means not very good vacuum. Very high vacuum is called very good vacuum. High. In pressures, high pressure is high pressure, low pressure is low pressure. But in vacuum, when you call, low pressure if you call, you are not making a mistake. But low vacuum means not, vacuum is reverse of pressure. So high vacuum is called low pressure. Please make that. And anything below atmosphere is vacuum. Anything above atmosphere is called high pressure. So as you go lower and lower, same 1000 molecules if you take, it will occupy 10 cc at 10 power minus 3 torr. Same 1000 molecules will occupy 10 meter cube in 10 power minus 9 torr, because mean free path is very high. PV is equal to nRT. P has gone down by N is constant for a number of structured molecules. R is constant. T is room temperature constant. Chamber is not heated. So if nRT is constant, PV must be constant. So P has gone down from 1000 millibar to 10 power minus 9. So 10 to the power of 13 times the volume has to go up. So like that you'll have to think. Okay, the volume unit itself has to be properly understood. This volume is not called physical volume. The equivalent volume accepts. All that will be there. I'm just giving you some, throwing some ideas, but this explanation I take 2 hours to explain for our BTech boys. So you'll have to be very careful. This is all the equipment that I'm giving you. The right side, if there is some problem, what is the problem? Here at left side I'm showing production, right side I'm showing last fellow troubleshooting. What is the trouble in a vacuum system? You don't get vacuum. If you don't get vacuum, no semiconductor manufacturing. So how do you do that? You can use some helium leak detector or residual gas analyzer. Even if there is no leak, if the ambience may be vacuum, but it contains oxygen, then it is bad. 10 power minus 5 torr, 5 millibar of oxygen ambience is bad, whereas 10 power minus 1 torr, even though it is poor vacuum, but it is argon or helium, inert gas, it is good because it does not interfere with your contamination problem. So parts per million thing has got a meaning if it is a dangerous fellow. And sometimes this oxygen is required in semiconductor manufacturing to intentionally oxidize silicon to formulate a silicon dioxide barrier, which to make a field effect transistor, you require silicon dioxide. And for making a micro nano capacitors, you require a silicon dioxide. So what is bad there, it becomes a good there. So all these controls require ultra high vacuum technology. So left side I have shown walls, lines, rough vacuum pumps, high vacuum pumps, chambers, leak detectors, analyzers. So I just want you to, all of you to spend half a minute to just look at it individually. Don't bother about your left or right. Go through the slide for 1 minute, half a minute. You will enjoy. I will come back after 1 minute. Okay, this is a typical equipment, but you require some time to understand. Those who are very serious in these technologies are doing really, are employed in semiconductor manufacturing, are trying to get jobs in semiconductor manufacturing. Please go through such courses. I keep on organizing such courses. not at all expensive. In our SV University and IIT, we all regularly do it. So if you can register through North Cap University, your names and all, if you can send me the list, I'll put you so that you can, some online courses also we can do, or in your colleges also we can do something like that. See, this is, I'm not advertising our course, but I'm just asking you to understand the concept. Unless you understand this properly, you will not be able to create manufacturing. You can create software, no problem. But if you want to manufacture, the processes are called clean processes, green processes. So if you do not produce vacuum, even if you are removing 99.99% from the ambience, you are far away from the purity requirements. I'm telling you, parts per million, 1 in 10 power 6, you have mode only 1 in 10 power 3. If there is oxygen not at all allowed, you have removed 99.9, but still that's not good enough. If you start processing it, you will get silicon dioxide, which is sand. It is not semiconductor. Silicon is a semiconductor. Doped silicon is a p-type semiconductor. Doped silicon is an n-type semiconductor. And if you can make it with an oxide layer again in between, that becomes a diode. And if you make diodes, two diodes back to back, that becomes transistor. And if you make two transistors, that becomes CMOS. And several such CMOSs, again with resistors, capacitors, will make a circuit. And several such circuits with necessary controls, etc., it will become a chip. And several such circuits are put in one die. Several such dies are there in 130 centimeters, say thousands of these things. Then you should know how to cut them with laser and diamond, etc. All has to be done very high precision, precise manufacturing, precise handling, precise cutting, precise packaging, precise deposition. Precision engineering is important. Don't get nervous. It's not at all difficult. Just it is removing the air. That's all. Okay. So this is how you should start thinking. Next slide, please. So we have understood the units of vacuum. We have understood the need of vacuum for deposition and because of long mean free path. And another thing which my predecessor has already explained, so I was lucky. If you try to do anything at 10 power minus 2 tar, within few milliseconds, one layer is formed. Impurity foreign layer is formed before you make one layer which is to be lithographed to make a PN junction. Already one oxide layer has been formed. That's called monolayer formation. It takes few milliseconds. Your experimental time is few hours before you close it and package it and put it into the chip. So during that time, the monolayer should take 10 hours. Only intentional layers, what you want to make should be the layers. Okay, this is also important. So concepts called molecular density, mean free path, time to form monolayer. These things vary from the level of vacuum. And you can imagine, those who are interested, you can just like that also tell mean free path. As pressure goes down, what will happen to mean free path? Can anybody tell? It will go down or go up? Mean free path. There are only two options. As the pressure is going down, vacuum levels are improving, the mean free path will increase, obviously, because number of molecules occupying in the same closed chamber is less now. Most of the molecules have been removed. So they are having more mean free path before colliding. Mean free path is defined not with the collision from the body of the chamber. It is defined with respect to their own collisions. Because body itself is 1 meter. What do you mean by 20 meter mean free path? Because molecules are colliding with body much more frequently compared to they themselves. That's why you will have straight line paths in the vacuum technology. So these are the concepts. I feel like talking about those concepts more, but unfortunately I'll have to go through the system design because they have given me the system design as the topic. Yeah, I should start from here, but without that basic knowledge, if I start from here, nothing will happen. Okay, so what do you mean by vacuum system design? I already told you must be an expert in production and what type of pumps, pumping speeds, etc. It's not only important to select a pump, but you should connect it properly. If you connect it with a capillary pipe, if your pumping speed of 1,000 liters per hour, 1,000 liters per second turbomolecular pump, it will come down to 0.1 liter per second because you have choked that. It is not pumping at all. So this is called conductance. You have a 10 volts battery, but a wooden stick, and then you put voltage. You will not get any concept. Current will not flow. the flow in the current means in our vacuum technology mass current, flow of molecules. So delta P is the potential V. So Ohm's law of vacuum technology is the throughput, which is current Q, is equal to delta P, voltage, into conductance of the pipe. Okay, just like V is equal to IR, the I here is I is equal to V by R. That if 1 by R is conductance, then it is V into C. So I is V into C. In vacuum technology, the I is throughput Q and C is C, flow conductance instead of electron conductance. And V is the potential drop, delta V, that is pressure drop here. So pressure drop, potential drop, mass current, electron current, electrical resistance, flow resistance. So all these things you have to calculate in the pumping speed calculations. And what are the materials to be used? That also system design fellow has to think. An engineer, if a boss says you purchase pumps, purchase valves, purchase gauges, purchase chambers, material, you have to decide whether it's stainless steel or iron or glass or that chamber, this wall, what wall. You get perplexed. There are codes for it. There are standard language for it. So you have to know that in the system design. I'm only giving various sub-blocks related to system design. Each block requires 2-3 hours teaching. Okay. Instrumentation and leak rate measurement. Now and then you'll have to see, just like a stethoscope a doctor uses to find the disease, then make it better. Similarly, we should know if there is a leak in such a complicated system, where is the leak? We don't know. For example, just show the next slide for a few minutes. Again, come back to this slide. Next slide, please. Yeah, just make this bottom figure little zoomed if you can. The other things are walls and flanges and typical laboratory units. But the actual semiconductor manufacturing or anything, that system will look like that. Can you zoom that figure? That Helmholtz, Gentrum, Berlin figure. It contains chambers. That figure only. Oh, okay. If it is unable to, if you want, if you can zoom, then they can appreciate better. I'm sorry for it, if possible. Otherwise, you say not possible. Possible. You are doing it. In your own screen, you can just put it, whichever is the control screen. If it is an expandable screen. Good. Make it full screen if possible. Great. Still. Even now it's more or less enough. Okay, enough. See, no, again, it was good. Make that left figure as much big as possible. Yeah, I think that's enough. Good, very good. See how many windows are there? All are vacuum compatible. There are couplings, walls, and I cannot explain from here everything. Gauges, control systems. What we are trying to do, there are several gauges, several throttle valves, several vacuum pumps are there, connections and the manipulators. From outside you try to do something, inside vacuum moves, X, Y, Z, tilt, rotation. The wafer is finally moving. With all these complicated things, what is it we are trying to do? We make that wafers in having several dies. Each die have got at a particular instant of time, whether a p-type or n-type, we are depositing or etching or doping or trying to do some operations. So those walls will be opened accordingly. That controls will be there. And whether it is happening or not, when electron beam is there, which will try to understand scanning electron microscopy, high energy, reflected energy. Parallelly, many people are just like when space shuttle is launched from Ahmedabad, several people are instantly, they are continuously watching the motion X, Y, Z, tilt, rotation type. Here, the observation is surface smoothness, where chemistry of it, residual gases, if there is any impurity, anything is there, immediately process will come. There is a lot of AML involved in making the controls, logics, which will make the electromagnetic controllers through an electro-pneumatic controllers, finally opening the walls, gas inlets, very high purity gases after monitoring thoroughly and entering into there, heating the temperatures inside the vacuum, then trying to deposit, and while depositing it is baked and PN junction is formed. All that has to be confirmed. Initial days, 50, 60 years back, they have done one PN junction. Here now we are doing million PN junctions parallelly. So you can imagine the controls that we are taking. Right side, we are showing different walls and high vacuum flanges. And instead of talking vacuum technology just for the sake of it, I'm trying to show you how it looks like, etc. Because that course itself is a detailed course. Some other time, if you are interested, you can call me anytime. We can give only vacuum technology, production, measurement, system design, nothing to do with semiconductor manufacturing. Then only you can learn those things, measurements. Okay, come back to the first slide now. So this slide we need not again show you. Just back, one slide back, please. And you have to also that flanges, you see how many nuts and bolts are there. Unless you tighten, there are no gaskets. The gaskets are itself metals. You have to cross the tensile, you have to cross that flow stress of that ultimate tensile stress of that gasket. Then it will make like a almost like two flanges welded. But you are not heating and welding. You are pressing so much pressure, atomic level, they are diffusing. So it becomes a joint. So it is not like a seal, it is a giant seal type thing. So all those things you have to understand when you are talking about ultra high vacuum, which is the state of the art now. Earlier, with normal vacuum, people have done, but today, as technology is going to micron to 10 nanometer to 1 nanometer, so how can you have 1 nanometer structure? Unless you make such controls of atoms. Okay. So that's why the low vacuum pumps, high vacuum pumps, process related gases, you have to check whether you have to have dry. Sometimes normal pumps may be allowed. If it is a rough vacuum chamber, you prepare the wafer and make it, dress it up neatly and neatly clean, and then more or less free from impurities from the atmosphere it has entered. So now from here, the next slide it will go. So that's where the growth. Then it will go to the analytical chamber. All that you'll have to understand. How do you connect them with various walls? So environmental constraints are there, corrosion. At the end, you are in this closed room. Any charge accumulation, you will get shock. Any fire accident, you have to be very careful. So clean room, it's not enough. Clean room must be safe room. Okay, you must, if oxygen has gone down below a level, people are not there to use these chips. Okay, so you have to be careful, and the controllers are there, monitors have to be there, and the design, for example, leak rate, VDP by DT. That means what? That much volume. You don't switch on the pump, close the pump with a valve, pressure will rise because of leak. If it is an ideal chamber, after evacuating and after closing, if you remove the isolate the pump, pressure rise will not be there. There's a designer. There will be one employee meant for only leak testing. So he has to take care of VDP by DT, the throughput, Ohm's law of vacuum technology, Q is equal to S into delta P. So he has to decide what is the pipe length, what is this, and what are the seal strengths, what should be the production of that seals, who will produce that seals, who will make that nut and bolts tighten, and what is the torque, mechanical engineers, electrical engineers. In fact, 90% of the job in semiconductor manufacturing is 99% is not at all electronic engineers. The semiconductor manufacturing, electronic and other aspects come only in 1%. Most of it is mechanical engineering, electrical engineering, and chemical engineering, and physics, and instrumentation, and chemistry, I'm telling you. So you later at your free time, or I'll just give you half a minute, see all the blocks once by your own eyes. Then I'll come back to the next slide. Just half a minute I'm giving you. Just see all the blocks. That's enough. Okay, I assume you have gone through it, but you may not understand every aspect of it, nor it is possible for me to explain. But some other time, those who are very seriously interested, those whose lifeline is linked to semiconductor manufacturing, please approach us. Next slide, please. Because you should Designing is important. If you make a wrong design, you have purchased 1 crore rupee pump, you have purchased 10 crore rupees of vacuum chambers, electron beam, high voltage units, and high frequency RF generators, but you are connected with a 100 rupee pipe which is badly designed. Then instead of doing the experiments in one day, it will take 10 days. So production rate comes down heavily just because you made a mistake in the design aspect of it. So design is different. Purchasing equipment is different. Okay. So there are different vacuum chambers, walls, components, seals, flanges, pipes, all of them manipulators, X, Y, Z, tilt and rotation through bellows. How can you manipulate inside? You can't put your hand into the vacuum chamber through the wall. But through the wall, there will be some places here and there you will see some bellows type thing which is sealed again, but you can tilt like this. The bellows means flexible pipe. So pneumatically it is not, it is connected to the vacuum. It is disconnected from the atmosphere, but mechanically if you float inside it will move like this. So these are called manipulators. Very high quality XYZ tilt rotation. If you can make that manipulators with precision engineering today, it is possible very much in India. Each manipulator we are importing more than for 20 to 30 lakh rupees. It is a mechanical assembly just sitting on top of ultra high vacuum chamber. You can make it in 2 lakhs. But it requires some knowledge. It is basically like lathe machine, XY machine is there. But we have little more of various types of assemblies. We'll have to see that. Okay. So this I think I don't have to ask you to read again because we have seen enough. Next slide, please. But at the same time, you require some flexibility. You can't say, I will just make the pump sitting on the chamber. That's not physically possible. Then a sound will come. And in a clean room, this lubricating oil of the pump will be spoiling this. So you will have to keep some minimum distance. So connecting pipes diameter is increasing, conductance will be more, flow rate will be more. The efficiency of the pump, full capacity will be felt at the chamber. Otherwise, pump is very costly, but that means even if you get 1 volt to at the end of the wood, you will have to put 1000 volts. Then you will get 1 volt after the wood. So whereas if you put a copper wire, 1000 volts will come. So something like that you will have to do here also. So here, if you see, there is a central chamber. And from there, it will be transferred to everywhere. It is like, several morning, he will distribute labor workers. You do this, you do that, like that. So same thing when vapor is introduced. Each has got bottom turbomolecular pumps. Each is a chamber. Each is one process. So these are all, nowadays they are making the chambers like monolithic chambers. That means they are not welded chambers. In welding there will be leak. There will be degassing because metals degas. That rust or anything if it is there, under vacuum they will come, they will cue some impurities into the chamber. Instead of having PN junction, you will get a rusted PN junction. It will not behave like a 10 power minus 9th of a second 101 operation. Unless you do 10 power minus 9 of a second 101 operation, you can't take 1 gigahertz RAM. 1 gigahertz RAM means 10 to the power of minus 9th of a second, 0 to 1 transition is taking place. That means the mobility of the electron should be very good. That happens if you have a controlled deposition doping. That happens in ultra high vacuum when you make the process. So all these are interrelated. When you go back, work out back, you will understand all that. So different things, there are connected walls. Walls must be vacuum compatible. Nut and bolts have to be vacuum compatible. Each chamber has got their own dedicated vacuum systems, different levels of vacuum. And you just have to transfer this fellow, go there, get checked and come back. Go here, get deposited and come back. Like that, the controls are there with robots. Automatically, the manipulator will take there. This micro manipulators movement inside vacuum is a big vacuum mechanical engineering that is being done at various IITs, and the packaging is another big thing. So there are many things going on in various high-tech places, and today industries have got their own R&D laboratories and their own training programs. So again, this is called load lock chambers. You first lock it, make what is it you are trying to do? The wafer only you are trying. First take the wafer from this clean room, put it there, load lock chamber, lock it, load it and lock it, load lock chamber, heat, treat everything clean. and don't make it go back to the clean room again, go back to the process chamber, and from there to other chamber. This is called, all these things have to be connected in vacuum technology. So this wafers go through various vacuum levels for various operations, various analysis and packaging and testing. Finally, IV characteristics have to be tested in situ, then and there itself, whether PN junction is formed or not. What one PN junction, millions. And then some PN junctions are added to make one resistor or one AND gate, NAND gates. Several such gates are processed to make high-speed processors. So all these things have got fab design is parallelly coming. So these things are interrelated, but it's not just a 3-year BTech or 4-year BTech. It's an involved process. Mechanical, electrical, electronics, every fellow has got a role to play. Now, I don't want to read this. So please go through different levels of vacuum, etc. with contamination I have explained here. Again, I will give 1 minute because I have only 20 minutes more. So let us go fast little now. So please go through for 1 minute now. Read it for 1 minute for the sake of it. Okay, next slide, please. So when you make chip manufacturing, you have to be understanding the processes first. That is called deposition, or etching, or doping, or lithography, or handling the wafer to go through all these processes one by one under vacuum conditions, sometimes under vapor conditions, but subatmosphere, but different levels of vacuum with different chambers going here and there. So I am showing the process cycle again here. You have to do cleaning in vacuum chambers, diffusion in vacuum chamber, ion implantation, chemical mechanical planarization, fairly rough vacuum. But because once you deposit and once you etch, make a wells and deposit, what do you mean by depositing? One P junction, one P material. See, silicon wafer, bottom first, yesterday he has explained, all the transistor layers are over. Afterwards, which transistor to be connected to which? All the public is distributed, who has to be friendly, who has to be connected to whom. This interconnection layers are to hundreds of layers. So these are various architectures. So that's where you have to have wells. Yesterday he was discussing through that. You will have to etch, remove material and deposit. All this is what? After deposit, after making the basic building things. In fact, some people call that as the wafer level. But actually wafer is a pure silicon wafer. Afterwards, you make several circuits, identical circuits, all million. Each is one cell phone. Each small die, which is 1 millimeter by millimeter, is going into one cell phone. And afterwards, you have to, because initially it is deposited like a puppet, here and there, black, black, black. Each black spot is a big circuit having thousands of elements, transistors, resistors, capacitors. But you'll have to cut it, the diamond cutter. So each die has to be taken out and everything has to be done, tested inside vacuum and properly, otherwise at least neat atmosphere, and bring it to some place, put it and connect it by external connections, because world knows pins only. World does not understand transistors, etc. So the using some 12 pins, how do you make the multiplexing operation? That means factorial 12 type, 1 to 12 if you operate that connection, this kind. So varieties of interconnecting logics have to be worked out. That's why they're called logic gates, whether OR gate or AND gate, and several such AND gates to be processor. So all this technology of flip-flops, resistors based on gates, Gates are based on transistors and resistors. Entire design, hardware has to be done in nanoscale. And each is one chip. Parallelly, thousands of chips are manufactured in one shot. So that one wafer when comes out, some 10,000 cell phones circuits are there. Each looks like a dot, but actually it's a circuit containing several transistors. But such things are possible if the background 2.4 10 to the power of 19 molecules are there, oxygen, and they deposit in millisecond instead of our PN junctions, you will not get any chip. It will become a potato chip instead of IC chip. But unfortunately, potato chips are also dried under vacuum. So that is another food processing. Whenever we give lectures for food processing, we do that. So vacuum technology has got a wide application from potato chips to the IC chips to the space simulation to various BRC, atomic research particle colliders, largest LSC. Have you heard LSC, Large Hadron Collider? 27 kilometers of vacuum ring is there. Entire thing is under 10 power minus 9 torr. Thousands of pumps are connected and evacuating. Then only the ions will be, one ion will be going on head-on collision. It will create the Big Bang theory, etc. For which 8 countries are spending huge amount. That's called ITER, International Thermonuclear Experimental Reactor, for which there is an Institute of Plasma Research. There are several plasma institutes are available. And for small ions to hit under ultra high vacuum for 10 atoms or 10 ions, you have a VECC, you have a BARC, you have several atomic organizations. So you will have, and once our satellite goes more than 6 kilometers, rest of the millions of kilometers it is under ultra high vacuum. So all the thin films or whatever you are depositing on the solar panel, which is again solar cells are also required for making the chips. That's also chips. They are called polycrystalline. They are not as accurate as this. They are meant for power industry. But here we are talking electronic industry. We are making electrons to go fast at 10 power minus 9 seconds. From one end of the chip to the other end, do an operation of 0 or 1. Several such operations parallelly going on millions, so that we will get our speech or video signals are processed and coded and decoded according to the software which understands the machine language. This is a big story by itself. So, but everywhere, if you see, a lot of things are basically vacuum chambers, vacuum load locks, walls, connections, equipment, and if something goes wrong, leak detectors, troubleshooting equipment. But we are only trying to make nanoscale depositions, nanoscale etching, nanoscale doping, lithography, handling, cleaning, all these operations. But you have to have pumps, you have to have gauges, you have to have couplings, and proper design of the interconnecting pipe is very important. And the chambers have to be degassed thoroughly so that they don't produce junk gases. And after doing everything, when things are very neat, when the entire marriage pandal is very cleanly arranged, then only marriage starts. Then only semiconductor manufacturing starts. Before that, if you operate, instead of getting silicon chip, you will get silicon dioxide chip, which is called sand. Okay, that is the starting point of silicon again. From silicon sand only, silica sand, we got silicon wafers. Then we made single crystal wafers, all under vacuum. Then we made the deposition, cleaning, and lithography, etching, metallization, contacting, packaging, everything done. And in any process, if you put more oxygen than what is required, at times you have to have oxygen to make a capacitor. Just next to the transistor, there will be capacitor. In the chip contains capacitors, resistors, and transistors and diodes. It does not contain inductors only. The inductors are get connected outside in the motherboard. That's how you make the things. So there are lots in MEMS, etc. There are even the inductors are also possible. They are also thin film type of thing, meander lines. But in most of the IC chips, you don't have inductors. So if you do all that, if you see the right side, can you magnify that right side picture, please? Left side, I have shown the processes which I have discussed, and all the information is basically that. So modern semiconductor manufacturing, just zoom that right side picture. Still bigger, still bigger. You see, the TV, the display is also having semiconductor circuits, because It is nothing but LCDs, LEDs, plasma shield. That is again semiconductors are controlling the intensities, red and blue, etc. Then cell phones and touching sensors, capacitors. These are all again within chip related activities. And right side plasma TV. There are millions. At any time, only one spot is bright in your TV, I am telling you. But you see the total picture because it's traveling at 500 megahertz speed video signal. You cannot see. Your eye cannot, if your eyelid can open and close in nanosecond, you will see only one dot bright on the TV screen. So all this physics, material science, electronics, fab design, materials, mechanical engineering, understanding properly flow processes, clean gases, entire ecosystem has to be developed in semiconductor manufacturing. It is not just to an understanding one electronics or chip design or anything. So that for all these things, the base is vacuum technology. Then you will get chip with various things. This chip is done either in TV or mobile or cell phone. So come back to the original slide. So the modern, now I am reading that, you don't have to go through it. Modern semiconductor chip manufacturing involves several sophisticated clean processes on silicon wafer, and all these clean processes are basically vacuum technology related. Otherwise, you have to produce gases, 99.99999 purity gases, which is much more costlier than vacuum technology. And when you are putting all those things, you cannot heat. With the convective heat transfer is too high. In atmosphere, if you put only pure gases, namesake purity, but heat is gone. Heat has to be conserved, like a thermos flask concept. Vacuum plays an important role there. Vacuum reduces the melting point and boiling points. And that's how you make the deposition. Why it is deposited under vacuum? You are melting the silver and it goes up. In thermal evaporation, it is like an agarbatti that we are using. You are heating a very hot spot, that vapor that comes out. That's called physical vapor deposition. It goes like this in agarbatti because of air molecules. Under vacuum, it will go straight. That's why it's called physical vapor deposition. Similarly, sputtering. It is like people, when you go to the temple, you scratch that 5 nanoparticles of that Shiva and all, you see, that vibhuti, and put it like this. That is called sputtering. So ion beams, which are like my nails, which are accelerated under vacuum condition. How this ion is produced? First electron has to be produced. How this electron is produced? Again in vacuum technology by heating a filament. These electrons have to be accelerated by high voltage. Finally, ions are produced. These ions are scratching like machine tools and producing a sputtered things. And these ions should not escape to the body and discharge. You have to apply magnetic fields to make a magnetron sputtering. So electron beam also can be used to focus it. Entire material silicon will be room temperature. One spot will be very hot. Just like eye surgery, when you do laser, one spot will be going to 1000 degrees. Entire eye will be very cold. So same principles are used here. If you do all that, only you will get semiconductor manufacturing, which is intrinsically related to vacuum technology. Next slide, please. So the Indian semiconductor mission, this is nothing, this is only a popular slide. They have made more than 86,000 crores for the entire industry. But even for research laboratories also, they have given a lot of money. And they are also giving quantum and all, same technologies, vacuum and other things are there for quantum chip or this chip. All are same, basically logic circuits only. So all these mission programs are there. If you are entering into either solar mission or a nuclear mission or a space mission or a semiconductor mission or quantum mission, you have got enormous amount of fund. Those who are in the industries, they can get more fund for their R&D. Those who are in the education institutes, they can get. Those who are students, they can get lot of jobs if you understand these fundamentals from class 11 to class 18 still up to PhD. If you are understanding, there are quite a good number of jobs. That's all. So I want you to just read this slide once for half a minute. All of you, please read it. Otherwise, I will read it for you. Specialized independent business division within the Digital India Corporation that aims to build a vibrant semiconductor and display. Because if you cannot see the display, that's also semiconductor basically. In addition, optoelectronics, but optoelectronics control is semiconductors backside. Okay, LCD, LED, etc. And this is coming in a very big way. It is a big global hub for electronics, because if only by suddenly people decide to stop chip manufacturing or giving the exporting the chip manufacturing to India, we will be in very big trouble. One full year we will not have any cell phone. Can we imagine that? Can we imagine without TV, without cell phone, laptop on one full year? Not even few minutes. So better be careful, understand this high tech, apart from BTech, MTech, and development of semiconductor and display manufacturing is the need of the hour. And I have given NPTEL course related to one aspect of semiconductor. We have also done other courses, but that you can find from NPTEL course that it is given there, and you can contact me at any time. With this, next slide, please. Thank you very much. I don't think I have covered everything, but what to do? It's a vacuum is vacuum.
Thank you, sir.
It
Thank
is
you so
empty.
much. Really thankful for sharing insights with our participants. So the chat box is open for sharing any questions you are requested, and feel free to interact with sir. So there was one question, if I may share from the chat box. So one of the questions says from a participant, is there any simulation software that we can use to check before we select the connectors and valves?
Yeah, there are, it's actually high vacuum design is not difficult at all. Idea is to select the proper pumps, selection criteria of pumps, selection criteria of gauges, selection criteria of interconnecting pipes. All these things are equation oriented. You can easily develop your own things. Don't bother about black box type of simulation softwares. You just try to imagine yourself and try to get the requirement need. I will give you the, I will make you simulate the thing.
Okay.
It is very easy.
Yes. So, if anyone wishes to ask more questions, you can just raise your hands or post in the chat box.
Actually, more of a care is important. If you put 1 cc of sweat, if you are cleaning up a vacuum chamber, by chance you are putting 1 cc of sweat, it will produce 10 billion liters of water vapor at 10 power minus 9 torr. So the way you handle the vacuum systems is more important. It's more of a skill development. Yeah, please. Space is perfect vacuum. Yes, you are correct. But we have to go to the space to do the experiments. At that time, we need oxygen. So if we can keep oxygen and if we can go, definitely billions of dollars that we are spending on producing vacuum and chambers and measuring is freely available in infinite space. But the problem is we will not be there to use it. We will not be there to enjoy it. Nature is always powerful. In fact, what we do in crores of rupees on earth is naturally available in millions of meter cube space available. In fact, liquid nitrogen, liquid helium is minus 269 degrees. It is very difficult. But if you go to the interstellar spaces, etc., there is a ocean of liquid nitrogen. So whatever we think you are trying to manufacture here, millions of times the same manufactured items are naturally available in the earth, but we will have to go to that.
Any more questions from the participant? Participants are really thankful for the passionate drive, as well as we also. So on behalf
Thank you so
of
much.
the entire organizing committee as well as our department,
Yeah.
sir, we are really thankful. So some more questions are also coming. So in a multi-chamber semiconductor vacuum system, how do conductance losses through walls and pipelines affect the effective pumping speed and the process chamber?
Excellent. Actually, each chamber in the multi-chamber has got its own dedicated vacuum systems. So we need to worry about that particular system, that particular pump independently. But when you open it to transfer the vapor from here and there, when we are having -8 tar one place and -6 tar, we are not interested in pumping one chamber through another chamber. We only transfer this, and it takes 1 hour for the two vacuums to come to equilibrium. In high pressure, it takes 1 second to come to equilibrium. But in high vacuum conditions, it will take 1 hour. But we will take only 1 minute to transfer the thing and then do the job and come back. So that way, mutual interference is not there, and there is no question of pumping one system through other system. Every fellow has got their own dedicated things, like in a multi-stored this one hotels and multi-stored various rooms in the same floor. Every fellow has got their own AC if it is possible. Otherwise, they can have a centralized AC. But when you put centralized AC, last room fellow will not get proper flow. These problems are there. Whereas in normal things in high vacuum technology, depending on the vacuum levels of that and the purity requirements, independent vacuum systems are designed. It's not a big issue, but you are correct. But in case you have to do such connections in between, conductance has to be worked out. In molecular flow conductance, the equation is very simple: 10 d cube by L. D is the diameter, L is the thing. And low pressures, it is, you don't have to bother about low pressures, low vacuum, that is high pressures, that is up to 10 millibar, 100 millibar. The first evacuation, virgin evacuation, where 99.9%, even if you make a mistake, instead of 10 minutes, it will take 1 hour. But if you make a mistake in high vacuum, instead of 1 day, it will take 100 days. Because the conductances in the molecular flow, few molecules going itself is enough to pass pressure drop. So you'll have to, the 99 runs anybody can hit. The last run is extremely difficult. The award goes from $100 to $1,000. Why? From 90th run also, there were some companies which are giving, after 90 runs, blood pressure goes to all the 12,000 people. And in the last 99th run, there were several occasions people got out. And 2 days, people got almost heart attacks, many people. Same story in vacuum technology. 99% of the air can be removed in 10,000 rupee pump. If you want to do 99.9%, you'll have to spend 1 lakh. And if you want to do starting step of a semiconductor manufacturing, you have to do 99.9999. That requires 10 lakhs. And if you want to do ultra 1 nanometer type, it will go to 7 nines. That requires, it's only 99.9, say 99.99. Hardly matters for us in terms of mass. But that last 4 nines makes it from 10,000 rupee to 20 crore rupees. That pumps. So if you manufacture those pumps or gauges or conductances, designs, if you made after all that cost, if you make a system design fault of using a small useless pipe, which is only 400 rupees SS pipe, you are losing hundreds of crores of rupees pumps efficiency. Instead of having 100 meter cube per hour, you have got 1 meter cube. If another intelligent engineer has made the same costly pump, but he connected properly, he will get 10 times faster the production rate. He will be getting 10 times promotion, and he will be there in the bottom. You will get demotion. So design is important. At the same time, skill is important, care is important, understanding the physics and engineering aspects is also important. Calculations are not a problem.
I think all the questions have been taken now. So I think this is it. We have taken all the questions from the chat.
Yeah, you can send me my WhatsApp message. Everything is given to them.
Yes.
So you can write any amount. I am 70 years old. I have enough time. I don't know how long, but now I am totally free. So you can write any questions. I can answer. I will try to answer. Otherwise, let us together answer, so that it is useful to the fourth person. And if you are doing a very good job, even a small good job, it is publishable today, because many people don't know. I am telling you. Small is beautiful. Ultra high vacuum is very, very beautiful. And it is required for all high techs.
Sir, one more question has also come.
Yes.
So in high vacuum systems, we often encounter virtual leaks caused by trapped air in blind tapped holes or overlapping joints.
Yes.
Beyond
That is called
printed
conductance.
screws. Yeah.
Yes.
Are there
Yeah,
any
when thread
modern
is
solutions?
given to handle some heating element, That thread was originally at atmospheric pressure. The last thread, pitch, whatever is there, the air is locked. That will take 1 year to come through that sled and goes to this chamber and finally go through the connecting pipe into the chamber. But meanwhile, it will is good enough to spoil these things. So what they do is even the drilled holes, that threads, etc. In center of the nut, there will be hole, so that the back of that mechanically it is threaded, but backside is pneumatically connected to the front. This is also important. And another thing which is a side branch of this, degassing. The surfaces which are there, they don't smell. But under high vacuum, they smell, they give out. And there is a permeation all the way from the outside, they will come through the leaks. And the manufacturing of the stainless steel sheet with which we are making a chamber, that contains some diffused gases in the original manufacturing. If you are choosing proper SS316, if you have not taken, those gases will slowly come out in the 10th run or 11th run. They will just come out into the chamber. So that is another thing. You can do the chemical analysis by in situ, by residual gas analyzer, which is connected automatically to the same vacuum chamber. Because all this X-ray, SEM, EDAX, they want vacuum. Why can't use the common vacuum for everybody? I have my own producer, I have my own analyzer, I have my own measurement. So that side of advantage is given in multiply connected systems. Pressure measurement, vacuum chamber, process, troubleshooting, chemical analysis, application, everything in the same place. After doing everything, you're giving, that's called reliability analysis. There is a journal called Microelectronic Reliability, Statistical Analysis. So many things are going on. With AML, lots of controls have come. If you are very intelligent, spend 1 year coolly in your room, AML software related controllers for pneumatic operations and ultra vacuum. You will get a very good paper and you will be called in America for a very good job.
I think all the questions are answered. Thank you very much.
Yeah, please give them my mobile number as well as WhatsApp
Yes.
number, etc.
Yes, sure.
Please distribute the slides to all of them, and we'll see whether how many people are coming back as interested persons and how many people get a career out of this. I wish all
Surely,
of you
sir.
get very good career.
Surely, sir. Thank you so much. And the way your presentations have been, you've been continuously supporting us, and the analogies which you give, I always, they make things simpler for us. There are very good number of students also participating, research scholars also. I hope everyone agrees with me, and we can see that in the chat box also. Thank you once again. So I
Thank you. I
request.
enjoyed interacting.
Thank you. So I request Shivam and Kashvi to please take it forward.
Thank you, sir, for sharing such deep insights drawn from decades of academic, research, and industry experience.
Your session provided participants with a strong understanding of vacuum systems and their central role in semiconductor fabrication. We sincerely appreciate your valuable contribution.
Thank you very much. Thank you.
Thank you, sir.
Before we conclude
Let
today's
us
session,
all make this manufacturing very enjoyable game.
The participants are really appreciating the enthusiasm.
Oh, thank you so much. Thank you.
Thank
All
you,
of
sir.
you.
Thank you so
Wish
much.
you all best, all the best. Thank you so much. Bye.
Thank you
Thank
so
you, sir.
much, sir.
thank you, sir.
Thank you. Thank you to all the participants. And we will meet tomorrow with technical session. 2 other sessions will also be there, and we will start at 6:30 tomorrow. So I will share the schedule on the WhatsApp group as well as in the email. Thank you once again, sir. Good night.
Thank you. Good night. All of you
Good
take
night.
rest. Relax.